You who are here. Thanks so much. Thank you so much for joining uh, our weekly webinar replay with our esteemed teacher Elaine Ingham. So we're going to get started in a minute. I see a bunch of people. Alicia said hello. Thank you so much for joining. Hello back to you. Um, and be just a minute before we get started. If you enjoyed our previous presentation, you'll surely like this one, guaranteed. Um, and also, this one is also a long video, so it's going to be about an hour and a half uh, today, and then we're going to continue this video for another hour and a half um, next week of the same video because this is a total of 3 hour for this session, this episode, and that is way too long for our sessions. So we break it down into two parts, into two videos, so that you have enough time, and also you need time to digest this stuff, get this in, and apply this into your own um, farming or whatever you're doing. So anyhow, let's get started. Once again, this is Dr. Elaine Ingham and Soil Food Web.
Okay, we're recording right now. Fantastic. So hey everybody, my name is Raleigh Latham. I am very excited and very grateful to be joined here with Dr. Elaine Ingham. Neil Spackman and I started an organization called Sustainable Design Masterclass. We do weekly webinars about regenerative design that are designed to help farmers, people who are passionate about environmental restoration, permaculture entrepreneurs, basically anyone who wants to tie their livelihood into restoring the environment and making money doing it. So we're very pleased to have Elaine Ingham on today. But before I let Neil introduce her, we've got to make sure that to get the most out of this webinar, turn off your Facebook. I know some of you guys have that open. Turn off your phones. Turn off all the distractions because there's going to be a lot of information flying your way. It's going to be a fire hose of pure, amazing knowledge, and you're going to want to be present for it. So turn off the distractions, and now I'm going to turn this over to Neil Spackman to introduce Elaine.
Welcome everybody to Sustainable Design Masterclass. Just to add to something Raleigh said, we are going to hold all questions to the end of the presentation. So I recommend you take notes and then submit your questions after, because we're probably going to max out around 500 or 600 people live, and if you ask a question now, it's just going to get lost in the text. So hold them until the end. I'm really happy to have Elaine and Raleigh here with me. Matt Powers was also supposed to be with us, but he had some last-minute things come up and was unable to attend. So he excuses himself. Dr. Elaine Ingham received her PhD from the Colorado State University in 1981 in microbiology with an emphasis in soil sciences. In 2011, she was the chief scientist at the Rodale Institute, and then after that, she became the founder of Soil Food Web Incorporated, where she continues as the president today, and she's also the director of research at the Environmental Celebration Institute. We're really pleased all of you could come today to attend, and Elaine, we're so happy you could come back on today, and I'm going to turn it over to you.
Okay, thank you very much, Neil and Raleigh, for getting this all organized, putting things together. Actually, I just wanted to do one little correction. I started Soil Food Web Incorporated in 1996. So I've been president of that since that time. When I was at Rodale, I just kind of put Soil Food Web incorporated to less importance and concentrated on Rodale. But when I left Rodale, then I have come back to Soil Food Web, working with people around the world. We have laboratories in a number of places around the world, and what we're really trying to do is train people to use the microscopes so you can do the work yourself. When you look through the microscope, it takes a little bit of training to get comfortable, but we of course have the online course for that, so you can learn. And then we do have practice classes at the farm here in California. So the research farm is here in California, just outside of Oroville, up in the mountains. It's a gorgeous place to be, and we've been doing research there for the last two years, because so often I have worked with growers where I come out and get a small amount of their land, an acre, 10 acres, or 100 acres, something like that, and we start doing the biological improvements of their dirt, turning it back into soil. And as soon as the farmer sees how easy this is and how much less expensive, typically today I will show you some of the results that we've had working with people in Australia on this conversion process, where we could actually have the replicated data being produced. But in the first year of working with pasture operations, we will save the grower over $200,000 in that first year, because I'll go through all the reasons when we get to that example. So if I could have the next slide, please.
Sure. Oh, as a quick check-in, just going to make sure, can everybody see the first slide of the presentation where it says from barren ground to fertile soil? Just a quick check. Put some ones if you can see that fine. Then we're going to get started. Okay, pretty much all of you are saying yes, maybe exception for one, but great. All right, Elaine, I'm going to turn it over to you, and
Okay.
let's get started.
Okay, so the first picture there, I don't think I can control the slides. Is that right, Raleigh? You have to do that.
Yeah, just tell me which slide you'd like to go to.
Okay, just back up one to that calendar picture of me in the Soil Food Web. There we go. So I like to start here because this does give a kind of that overall kind of a practical view of being out working in the soil, and hopefully this is soil. And we're going to go through how we define soil as opposed to, if you will, barren ground, or dirt is the soil science term for where we don't have these processes occurring. Soil, of course, you have to have those processes, and the organisms that do that processing, the things that do the work in soil, is all of this life. And so talking about, of course, the plants, the bacteria, the fungi, protozoa, nematodes, microarthropods, the larger critters, the macroarthropods, the spiders, and then go on to even larger things, voles and shrews and mice and birds, and the whole food web. And of course, who's the top of the food web? Well, we are, as human beings, really. We can do a lot of management, some of it not so good, where we don't really understand what the damage is that we're doing to the soil, and we have to understand that. If you read the book by David Montgomery, it's called Dirt, the Erosion of Civilizations. It's when human beings don't understand what is in the soil and the effects of their management on that soil, then we damage that soil, and pretty soon you've got dirt, or barren ground is another term for that. So I like this calendar picture where this is the lexicon of sustainability, and every year they choose 12 people for the calendar pictures, and I happen to be the very first picture that they chose in their very first calendar. So I feel honored that they would do that, that I would be the poster child. But it does put across a lot of information, and it's a very group to look at. So if we can go on to the next picture. Next slide. The next slide is the soil food web. When I was working at Oregon State University as a professor, the USDA came to me and asked if they couldn't have me help put together a soil biology primer. And there are, if I remember correctly, there are something like 7 or 8 chapters in the soil biology primer, and I wrote 5 out of the 7. So the basic introduction to the soil food web, the concepts, the principles of ecology, and then going through and describing bacteria, fungi, protozoa, and nematodes. And of course, my husband is a nematologist, so I picked on him a lot to help me with that chapter. Andy Moldinki wrote the chapter on microarthropods, and Dr. Clive Edwards at Ohio State University wrote the chapter on earthworms. So one of the best-selling books they've ever had in the USDA books that they sell. So when we look at this soil food web, to just briefly go over the roles and functions of each of these organisms, and I know I did this more, in more detail in the first lecture, but I want to remind everybody of the things that these organisms do. And so here we're looking at what a healthy food web will do for the grower. If we get the right sets of bacteria and fungi into that soil, there is a competition and maybe even sometimes an inhibition. All our favorite antibiotic producing microorganisms that we use for antibiotics for human beings come from soil biology. We've selected those organisms, grown them up to high numbers, so we're doing some unusual things to make an antibiotic high enough concentration to affect humans. But in the soil, in very small spatial areas, these bacteria and some fungi too are producing these antibiotics. And so there is inhibition. And of course, your plant is putting out exudates to grow these organisms when the plant needs that kind of help. Right there at the soil, at the root surface, there's inhibition. And then, of course, we need to have the things that consume the disease-causing organism. So we need the protozoa, we need the bacterial-feeding nematodes, the fungal-feeding nematodes to help suppress those diseases, and making certain that we have this massive diversity of all of these organisms that will do the suppression, will do competition, preventing the diseases and the pests and the parasites from having any food, from having any space, from having any control within that environment next to your root system or above ground on the foliar parts of your plant. We can pretty much take care of any diseases, pests, or parasites that you want to talk about. So instead of putting out these preventative toxic chemicals to prevent these problems, what we need to be doing is making sure we have all of this beneficial life surrounding our plants. We need to put those organisms back. If you're lacking those organisms, you need to go out and put them back. So where are the sources of those kinds of organisms? Well, we've got to be making compost. We're going to take organic matter, which already has all of these microorganisms on it. We've just got to make sure the habitat we are growing them in now is going to be beneficial for them. They can grow and multiply, so then when we put them out on our fields, they'll be able to do their jobs in that soil or on the foliage or around the root systems. So toxic chemicals, not necessary if we have the proper biology in the soil. When we're looking at what retains nutrients in the soil, it is the bacteria and fungi that will take up all these soluble nutrients and tie them up and hold them in their biomass. So think about the plant putting out exudates. Ooh, what's an exudate? For those of you who didn't listen in previously, what's an exudate? That's kind of, the scientific secret language. What do you mean when you say an exudates? All plants put out materials, organic materials, that are basically cakes and cookies. Exudates are mostly sugars, a little bit of protein, a little bit of carbohydrate, and if you really understand what those things are, sugars and proteins and carbohydrates, they are basically the building blocks of cakes and cookies. think of all the different kinds of cakes and cookies that exist on this planet, and your plant will put out the specific cake or cookie or combination thereof to grow these specific organisms that perform these jobs in soil, that suppress the diseases, that compete with the bad guys, that consume the bad guys. The bacteria and fungi, the plant is feeding those bacteria and fungi, so the bacteria and fungi will suck up any excess nutrients that are running around in a soluble form and keep them right there next to the root system. Now, the plant can't use the nutrients that are tied up in the bacteria and fungi. And in many instances, the bacteria and fungi are putting out waste compounds that some other microorganism is going to use as food, and then retain those nutrients in those other bacteria and fungi in complex organic compounds that these organisms also condense. So retention of all these nutrients is going to happen, especially around the root system where there are more bacteria and fungi per gram of soil or per teaspoon of soil than any place else in the soil. So retaining those nutrients. Well, if you're retaining nutrients, you don't have any problems with runoff. Leaching is not going to occur. You're not going to have your soil washing down the hill and ending up in the surface waters, or the nutrients, the soluble nutrients, can't escape from the soil because they get taken up and held and retained in your soil. So all of this fuss we have about all of these nutrients running off from agricultural fields and increasing the concentrations of phosphorus and sulfur and magnesium and calcium and nitrogen is a huge one, huge problem, because we put on so much nitrogen fertilizer because we're putting on a soluble form of nitrogen. And of course, the first time it rains, or the first time you irrigate, that soluble nutrient is getting washed beyond the rooting zone of your plant, especially where we're imposing compaction on our soils when we till. Every time you till, you impose a compaction layer. At whatever depth your tillage equipment goes down to, you're imposing a compaction layer. And that means your roots can't go any deeper than that. That means the organisms that do can't grow any deeper than that, because the anaerobic organisms in soils, well, it's not soil if it's anaerobic, it's dirt. And so those organisms are not the ones that benefit your plants. So we want to make certain that we build structure in our soil. So the fourth point down there at the bottom, building soil structure, is only done by the microorganisms. No bacteria, I'm sorry, the rest of the system is not going to be able to function, because that's the building block to build microaggregates. Then you have to have fungi to build macroaggregates, and you start to have the airways and passageways that allow water and your roots to go deeper into the soil. If we build better soil structure so that our root systems can go down the 5 feet, the 10 feet, the 15, 20, 25 feet down into the soil, you don't have to worry about summer water. Your roots are going to get to it. That water is going to be held. You hold on to all of your springtime runoff. You hold on to all of your snow melt. All your dewfall is going to be retained in the soil. So building soil structure is critically important. And bacteria and fungi are the beginners, the starting point for building that structure. And of course, as the bacteria and fungi grow in the soil, you build structure. They're retaining nutrients. How do you get the nutrients out of the bacteria and fungi and back into a form that your plant requires? And what determines the speed at which those soluble nutrients are being released right in the root zone? Well, amazingly enough, it's your plant. And so the plant puts out the cakes and cookies to wake up the bacteria and fungi, to make the enzymes, to pull the nutrients out of the organic matter, and to pull the nutrients out of the crystalline structure of the sand, the silt, the clay, the rocks, the pebbles out of your bedrock. There is no soil on this planet that lacks the nutrients to grow plants. And so we need to realize that the whole real reason that the Green Revolution worked, and put that word in quotes, it worked only because we'd already destroyed the life in the soil. If you have good biology in the soil, and you put out an inorganic fertilizer, nothing happens. If your biology is good, it is of no benefit to your plants to put out that inorganic fertilizer. Inorganic fertilizer and you see your plants green up, you see your plants start growing faster, you don't have the right life in the soil. And that means you're going to have to pay that money. You're going to have to do that work to get your plants to grow the way they should have been growing if you had the right life in your soil. If you put the right life in your soil, the plants maintain that life. The organic matter in your soil maintains that life, and then you don't have to do that work. If you get the biology right in your soil, then we're going to select against all those very early successional plant species called weeds, and they're not a part of your life. You don't have to be putting on herbicides. You don't have that problem. Whereas if you don't get the right life in the soil and you don't balance things for the crop that you want, you're going to have weeds. And think of the time and effort that people use to try to get rid of that problem, when if we just understand soil life, if we move away from barren ground into life, we don't have to worry about those things at all. If I could have the next slide, please. So I think the next slide is coming.
You see it? It's how do we recover from this build soil?
Yeah, I'm not seeing it. There it goes.
Okay, good.
From this. So this is a picture of the Great Plains of the United States back in the Dust Bowl era, where through the tillage, through the overuse of high salt containing materials, i.e. Fertilizers of various kinds, manure, that the animals were fed inappropriate foods, and so the salts in that manure did a lot to destroy that biology. So this is not soil. This is dirt. And look at how much of it is blew away during the era of the early 1900s in the United States. The Great Plains lost 5 to 6 feet worth of the soil. And so what was the mechanism for removing it? It was the wind. Without the right life in the soil to hold that soil in place, the wind would pick it up and blow it off. Tons and tons, millions, thousands, hundreds of thousands of tons of soil blew into the Atlantic Ocean. And you can see where the soil used to be, the man sitting on top with the grass, and all of that has blown away. So think about the fertility of the Great Plains now. When we come back in and we start to try to put plants back into the system, we're working with materials that we're going to have to build that soil. And in order to do it, you have to get biology back into the soil. So if we look at the next slide, and I think my computer is, the linkage with me is a little bit slow, so it takes a few seconds for me to actually see the next slide.
You see here now, it's dirt and soil.
So when we're looking at that difference in definition between what is dirt and what is soil, and you'll see that dirt is just the mineral components, the sand, the silt, and clay, which is the breakdown, the size fractions of the mineral material that breaks down from rocks, from pebbles, from the bedrock. So that's the mineral component of your soil, and that's really what we mean when we say dirt. Soil, by definition, Hans Janny is the father of soil science, and he made this definition, where it's the mineral component, yes, the sand, the silt, the clay, but it has to include the organic matter, which is the food that feeds the microorganisms. And it is the aerobic organisms in that soil that are going to be doing the work, not the anaerobic organisms. Anaerobic organisms are the diseases, the pests, the problems, the parasites. They do very little, well, not completely nothing, but they do very little in building soil structure. And those anaerobic organisms will make some highly toxic materials that will kill your plant. If you allow that soil to be anaerobic, the roots cannot grow into that material if there are anaerobic processes happening. So if we keep going, understanding that difference between, so the next slide, if you would. The next slide, very good. When we look at, so the first three columns, the one that says nutrients and listing the different nutrients, major elements, minor elements, trace elements. The first column after that is limit in parts per million. So here's the range. Most agronomists are looking at a range of nutrient concentrations that are in the okay. You know, it's you have to be above 150 parts per million nitrogen. Probably don't want more than 1,000 parts per million nitrogen in your soil. And that's what any agronomist is going to use to help make recommendations of, do you need to put inorganic fertilizer on or do you not? So are they going to be recommending sulfur fertilizer? Are they going to recommend lime? Are they going to be recommending molybdenum or manganese? Here are the ranges that they're typically looking at. So the average is the next column. So that's kind of what they're aiming for, are nutrient concentrations like this. Where do they get this information? Why have they decided that this is the proper concentration of nutrients in your soil? Because if you go back 50 years, these desired levels or optimum element levels would be half of what's listed in the slide. Go back 150 years, and the values are going to be more than 10 times less. So why is the common attitude that you have to add more and more and more of these inorganic elements in order to grow your plants? It's gotten higher and higher over the years. Have our plants changed? Does our corn require more nitrogen, phosphorus, sulfur, magnesium, calcium, sodium, potassium, all of these elements? Do those plants require more? No. It's because we've lost more and more and more of the biology in the soil. Let's go to an old growth forest system and think about the fact that, and that's the fourth column in this picture. Think about old growth trees are taking out of the soil and storing in the biomass of the tree on an annual basis more of all these nutrients than any agricultural crop that you want to talk about. Those trees are removing from that soil on an annual basis more nutrients than you're harvesting and removing from any agricultural field. And yet those old growth forest trees manage to keep growing at that same high rate, year after year after year, with nobody putting on inorganic fertilizers. Nobody needs to be putting pesticides out in those old growth forests. And look at the nutrient concentrations in that soil. How can those plants stay alive? If you were an agronomist, or if you went out and you took a soil sample from an old growth forest and told your agronomist that you wanted to grow, name your crop, whichever one it might be, how ballistic would they go? They'd, oh my gosh, you have to put everything back into the soil. No, you don't. What you have to have is life. Because the bacteria and fungi are taking any soluble nutrient that the plant doesn't take up and storing that, soluble nutrients in that soil are going to be very low. And so on a second-by-second basis, as the bacteria and the fungi are eaten by the protozoa, nematodes, microarthropods, and higher critters, that releases these soluble nutrients right in the root zone for your plant to be able to just pull it inside that root zone, inside that root, without having to expend any energy at all. If you have the life in there, every second of every day, these nutrient concentrations are kept above the level that your plant requires. And if that concentration gets too high, the bacteria and fungi just take the excess up and store it in their bodies. So your plant is in control of its own life. We need to recognize that. Because when we keep overloading, we keep putting on these massively high concentrations of nutrients, we're killing that life. And so we are stuck in addicted mode. And we need to stop doing that, because these high levels of inorganic fertilizers that are going on our soils are not held. They're not kept in the soil. They leach, they run off into our water, and we're destroying water quality. That's what's going to take humanity out first, long before any lack of food becomes a real problem. We make more food, more than enough food to feed everybody on this planet. A good diet every day. If we would get the food to the people who are starving to death, we've got the food to feed them. What we're really lacking is the water. In the United States, in all parts of the world, we're contaminating, we're destroying water quality, and that's harming human beings. So how do you stop destroying water quality? You tie up your nutrients and you keep them in the soil where they're supposed to be. That means you must have bacteria, fungi, protozoa, nematodes, microarthropods. You need all of these organisms in the soil. So if we can go on to the next slide. Hopefully you're understanding all these factors of what the life does for you. And I want to do just a little bit. Last time I went through some just pictures of the microorganisms. This time, let's look at some videos so you get a feeling for how these organisms move. So if we could go ahead and do the first video, I think it's the bacteria video. We're going to take a sample of your soil, so a gram or a teaspoon of your.
Very quick, Elaine, was this protozoa or rotifer?
Wasn't there a bacteria one?
Yeah, it was, the titles were protozoa or rotifer, but
okay, protozoa. Do the protozoa. So we're going to look at the morphology, the way these guys move. So look at all the activity going on. Strand that you're looking at that goes through the center of that picture from lower left to upper right is a strand of fungal hyphae. And you can see that it's 4 to 5 times the diameter of the little bacteria. So the smallest little pinpoint things that are moving around, those are bacteria. The things that are moving faster, there's quite a few individuals of those cute little flagellates running around. And on occasion, oh, here we go, that big guy with the hairs at one end, that's a ciliate. These guys eat bacteria. Oop, there goes a flagellate, went from the bottom to the top. Higher magnification here. So we're looking at the cilia on the back end of that ciliate. And it eats bacteria. The creatures that are running around in that suspension are bacteria. Here we are at, this is at a magnification of about 400x. And we're looking again at ciliates and some flagellates running around. Now we're back down at 100x magnification, and that's an insect larva. You can see lots of the flagellates. You can see that there's some ciliates running around, lots of bacteria moving as well. But that insect larva is telling us that bad things are happening in this soil. This really probably shouldn't be defined as soil. Anaerobic. The insect larvae only occur when we're in reduced oxygen conditions. So anaerobic conditions, we're producing toxic materials, not highly beneficial to the growth of your plants. So lots of little bacteria in this particular picture. We're looking at the center of that picture is drying out. And so sometimes, it's kind of fun to look at the different things that you can see in that soil. So I think the next picture, the next video is the rotifers. So if we could take a look at that.
Okay, cool. Just a quick check. Did everybody see that video fine? So put some ones in if you saw it all right.
We can always go back through that last video, and I'll do some more explanation as it happens. I wish I had a pointer, but I don't, so I have to do the best. See that inchworm kind of organism? He's kind of poking around, looking for things. That's a rotifer. It looks a lot like an insect larva, and if you see these things in your soil, you ought to go, oh no, this isn't soil, this is dirt, because that rotifer or an insect larva or ciliates are telling you that your soil is anaerobic. Reduced oxygen, toxic materials are being made, but they're kind of cute organisms. You can see also in this picture there's a few aggregates, these lumps that are in color. In the past, this soil was really good, healthy soil, but some things happened to drive it anaerobic, to get compaction going. And so look at the little pinwheels on the top of his head. That is why we call this a rotifer. It has those pinwheels that it's using to pull the bacteria into its mouth. This guy will decide instantaneously whether he likes those bacteria and wants to eat them or spits them out. He doesn't like them. So he's going to zoom in here and just harvest, if you will, harvest all the bacteria within this area of what he likes. And you can just see him going to town, having a feast, eating those bacteria. The aggregates that we're looking at, that nice dark brown color, is in the past, we've had good bacteria, good fungi, especially fungi, condensing down some of the structurally complex organic compounds into more and more and more complex humic acids. You can see some honey color parts of these aggregates. And again, that is the bacteria and the fungi producing not quite as complex, not quite as condensed organic material in what's called fulvic acids. And the difference between humic and fulvic acids is just the molecular weight. How complex has that organic matter become? Okay, so that should be all of the videos, right, Raleigh? Great.
Yep, that's all the videos.
So now that I've had a chance to briefly go over the roles and functions of these organisms in the soil, and you've got to see just a flash of what these organisms look like when we're staring through a microscope, helping you, I hope, learn that it's not that difficult to pick out bacteria from fungi, from protozoa, from nematodes, from rotifers, or all these different organisms. It takes a little bit of training, but this is not rocket science. This is something that's a lot of fun to watch, and will amuse you for hours on end with what's going on in this support matrix under your feet, helping your plants grow. Now I want to go into some examples, much more practical part of the program here. So we're looking at a neighborhood in Boston and working with these groups, Harrington's Organics, harringtonorganics.com, the Boston Tree Preservation Group, so you can Google that group as well, and Safe Lawns. One of the owners of the Boston Tree Preservation, that's his yard in the background that you can see circled by that white circle. A year ago, his lawn looked like the other lawns, the other landscapes and the houses surrounding his. And what has he done? What change has happened? That here we are in mid-September, late September, and his lawn still looks very beautiful green. All of his trees, all of his shrubs, his garden in the back, there are no diseases, there are no pests. He didn't have any fungi, no aphids, no white flies, no mites, nothing attacking his plants. And yet when you look at the other houses in the neighborhood, they all of their bushes, all of their trees, all their shrubs, their lawns really don't look very good. And everybody thinks that that's normal for this time of year, but in fact it's not. What's wrong? What is missing in these other lawns? Why are the trees, you look at some of those trees across the road and you can see bare branches where different kinds of insect pests have attacked and completely eaten the leaves off. Underneath the electrical lines, you can see that every single one of those trees, those shrubby trees, have some kind of damage, some kind of disease problems. You look at the lawns, and all except for Peter's lawn there, nice bright and green on his lawn, but all the other lawns are looking brown, pretty unhappy. The grass is all dormant. It's gone dry and brown. And the only green plants that we're seeing in those lawns are the weeds. So what's the difference? A year ago, his lawn Peter's lawn, the one that's circled up there at the top right, his lawn looked just like the other lawns. And so when he was talking to Todd Harrington, myself, other people at the tree preservation at Safe Lawns, we were telling him that that didn't have to be the way. And he kind of went, well, I'm not sure that I believe you, so let's do a demonstration. Let's, put your money where your mouth is and show me that my lawn doesn't have to look all brown and unhappy and weedy, that I don't have to deal with all these insect pests and problems. Show me. What do you do exactly? So that's what I want to go through right now, is that whole process of taking one of these brown, unhappy lawns, the brown, unhappy, or the portions of the plants, the trees and the shrubs and the flowers and the gardens, and how do we make certain that these diseases and pests, these insect problems, aren't going to rear their ugly heads? What do you do exactly? Now, a lot of people that are growers, they grow corn, or they have huge pastures, or they have orchards. They often say, this is not an example. There's a waste of time for me to watch this. Well, no, it's not, because you're growing trees. If you're doing an orchard business, you're growing trees. And so exactly what we're doing with the trees in this example is what you want to do in your orchard. We're just going to expand the acreage, that's all. Those of you who are in pasture where you have grazing animals, well, that lawn is not that different from your pastures, from your rangeland. And so exactly the kinds of things we're doing here is what you need to do in the rangeland. Those of you who are vegetable growers, what we're going to do in the garden is exactly what you're going to do in your vegetable garden. Yeah, you've got a lot more of each individual crop, but a lot more acreage of each individual crop, but it's the same process. It's the same principles that you're going to apply. So whether we're applying it to 100 by 100 foot square lawn, or we're applying it to 100 acre by 100 acre, or 1,000 acre by 1,000 acre area, it's the same principles. It's the life we've got to get back into the soil. So I always like this as an example because it really goes over all of our different kinds of cropping systems. And we're going to apply the same management. So let's start off. A year ago, we went out to Peter's lawn and took samples. We took samples from around the trees. What's missing in that dirt, because a year ago it was dirt, he did not have the organic matter. He did not have the life in the soil to grow healthy anything. He thought he'd been doing well, but when you start looking at the organisms will be very clear about what's missing and what you need to put back. So we went out into his turf and we picked places that were very weedy, places that were bare. So all the different permutations went into the garden, and in the tomatoes, in the lettuce, in the all the different kinds of crops, took samples and looked at the biology. So the next slide is going to show us some of the data. And so I'm hello?
Okay, can you see that all right? Monitoring.
Okay, it hasn't changed for me yet.
Okay.
So hopefully soon. So, little pause. There we go, monitoring. So the first column is the date. So a year previous to that picture we were just looking at, we went out and sampled the soil and all the different types of vegetation that he had in his yard. The second column, we're looking at the fungal to bacterial biomass ratio, so F to B ratio, fungi to bacteria. And so in the first row, we're looking at 5 to 300, 5 micrograms of fungal biomass to 300 micrograms of bacteria, strongly bacterial dominated. We know in any of these systems, for any of these plants to be healthy, we have to be above 300 micrograms of fungi and 300 micrograms of bacteria. Those are the minimums. If you're not above that level, you are not playing with soil, you're playing with dirt. So tell me, is what was in his yard, no matter which type of vegetation we were taking that dirt from, was any of it actually soil? No. Every single part of his lawn, every part of his, underneath his shrubs, underneath his trees, underneath the veggies in his garden, it was strictly bacterial dominated. There wasn't enough fungi for any healthy plants to be growing. And isn't that exactly what we're seeing in the rest of that neighborhood? A year later, when he had fixed his biology, the rest of the lawns in the neighborhood were still looking pretty sad and ragged. And they don't need to be looking that way. But we've got to, step one, we've got to get that fungi above 300 micrograms. Yes, the bacteria are already there, but you're selecting for weeds. If you don't have the minimum levels of these organisms in your soil. The next column, P2N, that is protozoa to nematodes. That's not phosphorus to nitrogen ratio. This is protozoa to nematodes. Do you have the organisms in that soil that will eat the bacteria and eat the fungi and release nutrients in a plant available form? Well, there were no protozoa at all in any of the dirt in that yard. And so, of course, you're not cycling nutrients. So the plants are going to be unhealthy. They're going to be stressed. They are struggling constantly to get the nutrients that they require. With the nematode part, we had 4 root-feeding nematodes per gram of soil. There were no bacterial feeding nematodes. There were no fungal feeding nematodes. So again, no nutrient cycling is going on. Of course, your plants are going to be stressed. There were no predatory nematodes. The predatory nematodes are the ones that eat the root feeding nematodes. You're trying to get rid of the things that attack and consume the roots of your plants. You want those predatory nematodes in the system. You want mycorrhizal fungi on the root systems of the plants that require mycorrhizal fungi. And if you've got brassica, mustards, kale, cole crops, you want actinobacteria in that soil so that they will prevent those root-feeding nematodes from ever finding the root systems of those plants. And there were none in these soils. So of course you've got sick, unhealthy, unhappy plants. There was no difference in the biology in that dirt between where they were trying to grow grass, where they were trying to grow flowers, where they were trying to grow vegetables or trees or shrubs. And as you all remember, I hope, from last session, is you've got to have different balances of fungi to bacteria to select for the growth of grass or vegetables or flowers or shrubs or trees. And none of this was soil. So of course you had problems. So how are we going to fix it? So if you look at the next row, it says compost. In the autumn, so in October, late October or beginning of November, hopefully before snow flies, we want to put down the first application of this biology. And so you've got to make compost that you're growing these aerobic organisms in that compost. So recipes of how are you going to make certain that you have the bacterial foods and you have the fungal foods and you have the party foods to get the bacteria and fungi growing really fast so that they will feed the protozoa. So you will have the predatory nematodes that you want as well as the bacterial feeding and the fungal feeding nematodes. So you've got to make compost correctly. And again, we have an online course where we teach people how to do that. So the compost, you better look at it and make sure that it has the biology in it that you want. So here's our compost. They were looking at 250 micrograms of fungal biomass, 300 micrograms of bacterial biomass. Now, is that going to fix the dearth of fungi that were present in that soil? Well, no, because the fungi are lower than the bacteria. It's going to move you in the right direction, yes, but is it going to get you there with one application? No. So we added some additional fungal foods, the humic acids, that you can extract from your own compost. So you don't have to go out and buy humic acid. You want to make your own compost and then just using water, passively moving through that. You want to extract the humic acid, and then you add that into your compost pile so you can increase the fungi. You add the humic acid to the soil where you're putting on your compost. So the concentration of compost that we were putting on was 1 ton per acre. So this is a 100-foot by 100-foot square yard. So, we're putting on about 10 pounds of compost going onto this area. Doesn't seem like much, but it's an inoculum. These organisms grow. They're going to grow all winter long in the soil. Under the snow is the best time to grow these bacteria and fungi. Now go to the next column, protozoa. We're at 20,000, good, because we want 10,000 protozoa per gram, putting out 20,000 protozoa. So good, per gram going out there, good. We're getting that much on the surface of the soil. But there were no nematodes in that compost. Oops. We really needed better compost. You really need to be checking the compost that you're buying and making sure that it contains the biology that you want. If you're going to a municipal waste site, that's not compost. That's mulch at best. That's some pretty scary material most of the time. And we need to change that business in the United States, well, around the world. Don't get suckered in by somebody telling you that something is compost when it's really putrefied organic matter. Stinks to high heaven. It's black in color. No, that's not compost. We need to be checking that compost with a microscope. So learn how to use a microscope. In our notes, you can see that we added additional fungal foods, mulch. So ground up organic material, put that on the soil surface around the trees, around the shrubs. We added mycorrhizal spores because compost does not contain mycorrhizal spores. So we let that go through the winter time, kind of crossing our fingers, hoping that the organisms are going to be growing. And that's going to be good by the time we get to the end of the winter. So here we are, soil. If you look at the last row, on March 15, snow had pretty well melted, and the soil had become warm enough, so it was time to look at what happened. So here we are. You can see that our fungi in that soil had increased from 5 micrograms to 150. Woohoo! Good job. But is it high enough? Have we actually really set the stage to grow good grass, to grow good trees, to grow good veggies? No, not there yet, are we? Because we want it at least minimum 300 micrograms of fungal biomass and 300 micrograms of bacteria. Certainly where the trees are, we wanted that to increase that by a factor of 100. When we're looking at shrubs, we want to see that increase by a factor of 10. So nowhere have we achieved a healthy soil for any of the plants that we wanted to grow. So we're going to have to keep adding more. We're going to have to put more biology out there. The protozoa, the flagellates, so in the third column, F, that means flagellates. So we had 10,000 flagellates, 5,000 amoebae. Good, those are the aerobic protozoa, so that's gotten right up to where we need it to be. Good job. Nutrient cycling is going to be happening. No ciliates, that's what the C is for, no ciliates. But we only had bacterial feeding nematodes. Not going to be enough. We need to cycle the nutrients out of the fungi as well as the bacteria. So we've got a little more work to do. So if we can go on to the next slide, we'll continue going through this process and we'll talk about some of the pitfalls. So here we are in March. I said we need compost tea. So you've got to look at your compost. And they didn't look at the compost. They just assumed that the compost left over from last October was going to have the same number of organisms in it in March. What's the likelihood of that happening? This is life. Life is constantly responding to the habitat in which it's growing. So through the winter time, the compost pile froze. And then come springtime, the organisms start to wake up. And when we looked at, I made them go back and actually give me some of that compost. We looked at it and looked at the fungal to bacterial biomass ratio. that's pretty bad. There's no way to fix the problems that need to be fixed in these soils with that compost. Because look, the bacterial biomass, 1,000 as 125 fungi. This is the problem. The protozoa have gone down. They don't survive being frozen through the wintertime. We did pick up fungal feeding nematodes, so that's good. So it's not all bad news. But they made compost tea because come springtime, they just wanted to spray this out as a liquid. So they extracted these organisms from the compost into the water, and they added some foods to try to grow the organisms. They could have fixed the lack of fungi by putting in some really good fungal foods into that compost tea, but they didn't put enough. Because look at that fungal to bacterial ratio, 150 to 900, they went backwards. No protozoa, no nematodes. It was in, those organisms were in the compost, but they're not making it through the extraction process. There's something wrong with their tea brewer. They're hurting things more than they're benefiting. So when I saw the data, I said, add more fungal foods. When you put this compost tea out, put more fungal foods in there. Hopefully you get the 150 micrograms of fungi growing. And then you need to add protozoa. So we had made a protozoan infusion, but still no nematodes. So 2 weeks after that compost tea was applied, go out and look to see what actually happened. We know from looking at the soil on March 15 what we had. And 2 weeks later, here we are, the end of March, or excuse me, the end of April. We're looking at the soil again, and nothing's been fixed. Actually worse. That fungal to bacterial biomass ratio is worse than it was back at the end of winter. So, big sigh. We're going to have to go out and apply again. Couldn't we have done this with one application? If you pay attention to the organisms, you can, but you have to pay attention to the organisms. So if I can get the next slide, please. There we go. So we're looking at the compost tea for May. So we, 1st of May, making another compost tea, or we're looking at the compost that they're going to make the tea from. And again, it's just gotten worse. Their storage conditions are flat wrong for improving that fungi. They need to do something. So what they did, if you look in the second row, is to add more fungal foods. And so within a week, look at how much that fungal compost has come up. Okay, but we took out all the nematodes when you turn the pile. So, but the fungi and the bacteria have to be fixed first. The nematodes will come along. So they made tea from that compost, but you can see they still had problems with the tea brewer. They needed to go in and look at the way they were extracting. They still wiped out all of the protozoa, so they had to add a protozoan infusion. They applied that tea. Now let's look at the end of May. Have they gotten that soil where you want it to be? Well, both the bacteria and the fungi are well above 300. So, okay, but is the balance correct? The balance is getting close to what we need for the vegetables in the vegetable garden. Getting close for some of the flowering plants in the beds, but not adequate for your grass, not adequate for the shrubs, and not adequate fungal biomass for the trees. So gonna have to keep trying, keep working on it. This is getting to be quite a process, isn't it? I would have let them to have really good compost from the very beginning. But let's go ahead and look at the next slide. Did we ever get this fixed? Well, of course we did, because I showed you the picture at the end of the growing season. So they got it. They got the biology back in here the way it needs to be. But you can see it was probably more of a process than it needs to be. But I think it's a great example to show you that you have to have the right biology. So here we are in June. Looked at the compost that we had pre-treated a month ago with those fungal foods. Now, right away we saw an improvement in the fungi back in May, but here we are in June. Look at that fungal to bacterial biomass ratio. Yes! We are really going to bring the fungi along. We are going to pull things right up to where they need to be for the trees and the shrubs and for the grass also probably improving thing for the vegetables. So yes, this is finally compost the way we want it to be. Well, except we could use a little fungal feeding nematodes in here. But hey, we've got the fungi, we got the bacteria, we got the protozoa, we got the nematodes, except for the fungal feeding nematodes. Just one thing that we have to work on after this. So they extracted that compost and made tea. Yes, 500 fungal biomass to 300 bacteria. I'm still kind of suspicious that, you know, there's something going on with the pump because it's knocking down. We are not extracting the fungal or the bacterial biomass. Something's going on in there. So we're still going to add humic acids around the shrubs and the trees, fungal foods. Our protozoa are right where we want them to be. We've got bacterial feeding nematodes. So we applied the tea 1st of June. 2 weeks later, go out and take a look at what's going on with the biology in the soil. And yes, things are right in this soil. We've got the grass, equal biomass fungi and bacteria, way up above 300 micrograms, which is the minimum. The shrubs are on the fungal dominated side, so no diseases, no pests, no fungal problems, no aphids. The trees, not seeing any of the insect pests that are normally affecting the trees. Protozoa, and look, the fungal feeding nematodes and predatory nematodes that were in the soil have been attracted back and are doing their job. So that's why their lawn looked absolutely beautiful. So Peter always has a few jokes to make about, you know, here's his lawn, end of September, when there's watering restrictions because they were in the middle of a drought that year in Boston. And his lawn is beautiful green. Everybody's going, oh, you've got to be watering that. That's, you know, you're sneaking out there in the middle of the night watering your lawn. And he's, no, you know, we're not watering. We've just rebuilt soil structure, and every drop of dew, every little bit of rain that we're getting is going into the soil, and that's more than enough to maintain moisture for all of these plants. Everybody else's lawn, dry, brown, bad looking, really unhappy. So the police car, Peter said he would get up in the middle of the night, 2 a.m., and he'd look across the street, and there would be the police car hanging out, waiting, because they just knew that those sprinklers were going to be coming on because they had to be watering their lawn. And of course, the sprinklers never went on. He did not apply irrigation water to his lawn for the whole entire summer. How would you like to reduce your water payments? You don't have to be forking out a fortune to keep your plants in your yard or in your fields or in your pastures alive if you get the biology back into the soil. So let's go on to the next slide. Hopefully that's been a good explanation for you to understand these steps that you need to go through, and you can see where it is so important to be able to look at your soil and be able to say, well, there are no fungi in here. I got to work on that. Where am I going to find the fungi? And then go and check out the compost. Make your own compost. Make certain that the biology is in there that you need to have. So the next example is the Camperdown compost work that we did with this company just outside of Melbourne in Australia. So we're looking in southern Australia. The town of Camperdown is about an hour out of Melbourne to the east, to the west, sorry, to the west. And so Tony Evans and Nick Routson are the owners of this company. And if you want more information about these results, you can certainly contact Tony and Nick. Usually they're crazy busy in their summertime. Remember that it's late fall for them right now, and so they're going into their winter period, and so winter is a good time to try to get hold of them. When it's summertime, these guys are just crazy busy, and you'll understand why in just a few minutes. Next slide. So when we first started working with Camperdown Compost, they had a composting yard, and they were encouraging all these dairy people, all the farmers in the local vicinity, to bring their um, waste materials, any manure, any waste materials, any woody material they were chopping up. Uh, uh, did you switch to the next slide, Holly?
Right now we're on Andrew and Linda Wingham's farm.
Okay, it hasn't processed over yet on my screen. So
Okay.
In the first year, well, when we first started working with Tony and Nick, they had all of these growers bring their waste materials into the central location, into their composting yard. And then Nick and Tony turned it into really good compost, and I was helping them with the microscope work, and we were chatting back and forth. They were asking questions, and they were getting the composting part down really well. And then they thought they would be able to sell the compost back to all of these growers, and all of the dairy people, all of the row crops, the veggie guys said, we would really love to get the compost from you, but the transportation cost is too much. We can't afford it. And so Nick and Tony were like, oh, what do we do? So they sold all the compost into the communities in Melbourne. But they really wanted to help the growers local to them. So how are you going to be able to fix this problem? And my computer is still not going forward. So I've
What do you see at the moment?
Camperdown Compost Company, biological farming products. That's what I'm seeing.
Okay,
So
I'm on Reggie and Jeff Davis. Can you see that now?
Nope.
Okay.
Not coming through.
What about everybody else? Can you see the slide? It should say Reggie and Jeff Davis feature on landline 3/7/2011. Okay, everybody can see it. I apologize.
Okay.
Elaine's in a place with kind of slow internet, so.
Very slow, and it's getting worse. So I've just switched over to Andrew and Linda Whiting's farm. After they had this experience of none of the farmers could afford the transportation cost of the compost, this biological inoculum, back to their farm, we all sat down for a conference and we said, what do we do? And in an offhand moment, I said, well, why don't you take your equipment out to their farms? So load your turner, load your water wagon onto a flatbed truck and go out to their farm and go around to each of the farms and make their compost on site. And you just charge the growers for transportation of the turner. You know that you're going to be having exactly the same recipe of the compost because all of these guys, the eucalyptus, are making wood chips out of the eucalyptus, out of all of their hedgerows, plenty of woody material, plenty of green materials. You just harvest a little bit of your pasture, or you go to where you have leftover hay or take the bedding material out of the milking parlor, and you know exactly what the nitrogen, the green, the woody components are. And so from the day you start that windrow, you're going to come back in 2, maybe 3 days and turn it the first time. And then you're going to come back the next day and turn it. And then you come back 2 days later to turn, and you'll come back 3 days later. So you know that in the route that you have, you're going to be doing 15 to 20 farms with making compost on their property, and you're just making the rounds on a weekly basis. So on hopefully you guys are advancing. Seeing the Whiting's farm, you can see in the springtime what their farm looked like. And if you recall back to those pictures, you could see areas where they had bare patches within the pastures, where they had urine spots where the animals are pooping or peeing, and the nitrogen in those waste materials, in the urine and the manure, were increasing the growth of the plant. That's telling you you don't have the right biology in the soil to deal with problems. The nutrient cycling isn't adequate. And so when you have the cows urinating, that nitrogen allows the plant to grow better. It's a clue. It's a message from Mother Nature saying, you don't have the biology to fix this problem. Get the biology back in here and you won't have this problem. Because the animals will not eat that grass that has had urine or manure onto it. They know it's unbalanced, it's unhealthy for them to eat, and they don't touch it. So great, they're not eating what percentage of the grass in your pasture. On the Reggie and Jeff Davis picture, hopefully you were seeing all of the bare patches in there. You can see the little tufts of grass, but there was quite a bit of bare ground in between all of those tufts of grass. Off in the distance, you could see the weed patches in their pastures. And so how do you deal with those as a grower? When the animals walk into your pasture and they lean down and they take bite of the grass and they rip the root systems out along with the above ground part of the grass, that means in not too many years, you're going to end up with the problem of having to resow your pastures. And so the more toxic chemicals, the more inorganic fertilizers, all of the insect pests, all the cost involved in putting that material out was also preventing regrowth. Are you
Oh, there you
able to
are.
hear me?
Yeah, yeah, you're back on. So I was trying. Someone had their phone on that was unmuted, so I was just turning that off. So back to Elaine, everybody. Sorry about
Okay. So each year, the growers that were looking at their property here, they would have to pay um, hey, I'm unmuted again, so I'll keep going. Um, it just says I'm muted again. Okay. All right. Um, so each year they would have to resow some portion of their property, and that's very expensive to resow a pasture. On average, it would cost these fellows about $20,000 to resow the pastures, but you can see the size of the pastures. You're looking at dairy farms that were between 300 acres and about 1,000 acres. So I'm hoping you're going on to the next pictures. I need to catch up. There we
We're on Tim and Sally McLeod. Okay, you keep getting muted for some reason.
Yeah. Um, and in Tim and Sally McGlade's, you can see there's a lot of weeds, there's a lot of bare patches. So all of these farms are suffering fertility problems. Hopefully you've gone on to the next slide, which I think is a list of some of their problems, hopefully.
Yep, background
Yeah,
issues.
there you go. Background issues. The cost of the fertilizers that they were putting out were getting more and more expensive. They still are in most parts of the world, but it's not increasing the growth of the grass. It's not increasing the nutrient concentration. If anything, the nutrient concentration of their grasses were going down and down and down. So back 50 years ago, 25 years ago, the bricks in their grasses were up around 18, maybe 15. And when we started working with them, the bricks in their grasses, the percent solids, the proteins and the sugars in the grass were down around 1 or 2. So poor fertility and pouring on the inorganic fertilizers was making things worse, not better. The insect pressure on lucerne, that's alfalfa. The rest of the world calls it lucerne. The United States, we still call it alfalfa. But they had to use a massive amount of insecticides to be able to have that source of fodder for their animals through the winter. When the animals were out on pasture, they were pulling out the roots. So the massive cost it took to resow pasture every year they were having to resow. They were not having any clover in the field, so they had to put out the nitrogen fertilizers because there was no nitrogen fixation occurring in their pastures. Their animals were sick. They were, all of the guys we talked to were just close to ending it all. Either by so hopefully this is not going to mess things up. So can you hear me?
Yeah, so I think it's just a bandwidth issue on your end. Sorry, everybody. It's a tough thing doing this in a rural area, but we'll get through it. Right now we're on background issues. How about we move on to the next slide?
Yeah, go ahead on to the next slide. So the animals were sick, they were unhappy, the growers were, many of them went into dairying, into growing plants because they loved growing things, and they were just, their animals were sick, their families were sick, they were losing money, it was just time. And on top of that, along comes the EPA and says, you have no waste management plan. We told you, the Department of Agriculture in Australia had told these growers, the dairy guys, just big.
So everybody, we're having a bit of an issue with Elaine's audio. Her upload speed is a little bit low. Okay, try again, Elaine. How are you? Try talking now.
Okay, try that. We're looking at the area that they bring the animals in before they take them into the milking parlor. And so animals would be getting a little bit of food, and of course they're putting manure down. And so the next slide shows the manure being washed out into the manure lagoons. And they were told that by the time they filled up their first manure lagoon, that the authorities would have a way to deal with this waste material. And of course, they did not. So the next slide shows that the manure lagoon, this waste is all being pushed out into those lagoons. And you can see where one of the lagoons is completely full. The lagoon next to it is almost full. The liquid runoff from the solids, as they settle, they would pump the liquid material off, and you can see the high nitrate containing water. And they were told to water their pastures with that high nitrate containing material, which just made the biology in the soil die faster. And then all of the resulting problems in the pasture after that. So how are you going to deal with this? And then along comes the EPA, the Australian EPA, and they basically say, for every day you have waste materials sitting in these lagoons, we are going to fine you $15,000 a day. So they want these growers to get rid of the manure, but they give them no information on how to do that. So these growers just wanted to, throw up their hands and walk away. And so by coming to them and saying, look, take that manure and start building windrows. You've got the straw left over, you've got in the dairy barn, the material underneath the animals, the wood chips, the straw, the material that they urinate and poop in when they're in the dairy barns. You can take that material. You've got all the hedgerows. You've got the eucalyptus trees. You've got some plant material, weeds. Just mow the roadsides, and you can start to build compost piles. And you can empty out these manure lagoons. So the next slide shows as they're moving all of that material, and you could just imagine what this smells like. If you've ever been downwind from a manure lagoon, you don't want to think about eating lunch. The smell is just incredible. So instead of leaving that where it attracts all these flies, where the smell is horrible, where it causes disease in any animal that's downwind of it and smelling those anaerobic odors, take that material, next slide, you can see them putting the windrows out. So the grower themselves is taking this waste material, putting it into the windrows. So you see the manure going down. Now we're going to put woody material on top of that. We're going to put green material on top of that, and then just keep layering until we have those windrows up to about 4.5 to 5 feet in height. The grower then calls us up when they have all of the parts of the windrows, and the turner arrives the next day, runs through the windrows. So the next slide shows the windrow going through the pile of through the windrow. So the cylinder has teeth on the cylinder, and it throws the compost up into the air in the middle, moves the sides of that windrow into the middle, so you're getting proper movement. So all parts of this pile will spend long enough in the middle, hot part of this pile, to kill all the human pathogens, to kill all the plant pathogens, to kill all the weed seeds.
Elaine, I'm going to do one quick. It should boost your speed. I'm going to turn off your camera, so it'll just be your audio in the presentation. Is that fine? Okay, great. Can everybody still hear Elaine? Elaine, can you talk for me? No, people can't hear it. All right, no audio. All right, Elaine, I'm going to turn back on your camera. Oh, hopefully she didn't drop. You were muted. Okay, now we can hear you. Great. Can everybody hear it now? Awesome.
You can hear me. Great. Yay.
Right. Yay.
Okay, so you can see the turner going through the windrow. You can see some woody material, some straw or wood chips, sawdust that was put on the row. So as the turner goes through, it mixes it. We have water wagons, so we can put the water in the system. So if you go to the next slide, that compost was applied in the first year. One more thing. The grower has to measure temperature on a daily basis during the 15 days after we start turning the windrows. So that's all the grower has to do, is report on a daily basis what's the temperature in the pile. And typically we come back at 2 days after you start the piles, the next day, so 24 hours later, and then 48 hours after that we turn again, another 3 days after that, and then one more turn about 3 days after that. Then the pile cools down to ambient conditions. So this is a commitment of about 15 days of your life in order to make sure that this compost will compost correctly. It doesn't go too anaerobic. It gets turned, it gets cooled properly. All the pathogens, pests, weed seeds, etc. are dealt with. So the next slide. Why is composting needed? Because if you're putting manure out, you're putting all the diseases. All the parasites are not getting dealt with. You've got all the seed that is in the foods that the animals might be fed. All the weed seeds are in there. You've got root-feeding nematodes potentially. We need to concentrate and retain the nutrients in the biology so it doesn't leach, it's not lost when you put the material out. So next slide. Hopefully you can see why we have to compost it. Compost is the aerobic, so we have just the good guys, none of the bad guys. Now going back to that comprehension of competition, inhibition, and making certain that all the bad guys are dealt with. We've got to decompose that organic matter so we concentrate the nutrients. And that means you have to have bacteria and fungi. A lot of people just don't seem to realize decomposition doesn't happen unless you have the organisms that do that. And those are your bacteria and fungi. High diversity, so no matter what the conditions, we will have bacteria and fungi growing and doing their jobs. We have to have the protozoa and the nematodes in order to do the nutrient cycling. Once this gets into the soil and these organisms get in the root system, they will do the job that the plant expects them to do. And of course, build structure, all those beneficial things. So the next slide. Understanding starting materials. And so I touched on this just really briefly before. You have to have the party food. That's the high nitrogen. That's what stimulates the bacteria and fungi to start growing really fast. So the types of high nitrogen: legumes, manure, seed, materials like that. We've got to have green material going into the compost pile to grow bacteria. We have to have bacteria. So they help form structure, retain nutrients. So green plant material. If you harvested the plant when it's green, then you're going to retain those proteins and those sugars and those carbohydrates if you dry the material down and don't let any decomposition occur. Drying is the easiest way to shut everything down. Woody or brown material, of course, is fungal foods. And so, the types of things is woody plant material, paper, cardboard, all of those sorts of things. So next slide. If we're putting the proper ratios together, then our composting, we know exactly which days we're going to have to be out there with the turner in order to get the whole composting process done within a 21 to 28 day period. Things we've got to think about when we're doing composting: we can't be using water that contains chlorine or chloramine, so you've got to remove that chlorine and chloramine by adding a humic acid or any organic acid. We've got to cover the pile so it doesn't lose moisture, or if it rains, it doesn't get waterlogged, because you go waterlogged, you're anaerobic. We need to monitor temperature. We know what's happening with the moisture when we're coming in and turning on time. We're adding water when it needs to be added. We can't have anaerobic smells. That tells you it's going anaerobic. You're not maintaining conditions so the good guys are growing. So all of these factors, and again, you might really be interested in taking the compost course if you want to really do all of make good compost. Going on, next slide. So typical turning regime. So we're starting out at ambient conditions at day 0, and as the microorganisms start to grow, we've got enough moisture, we've got the foods in there, temperature gets up to around 160, 165, you have to turn. You're going anaerobic if you go over that temperature. So when you turn, it drops temperature, and here you are, a day later coming back in and turning again. And then you turn, drop the temperature, get oxygen back into the pile, maybe add moisture if you're starting to get too dry. And in 2 days, we're going to come back and turn again. And so this is a very typical turning schedule for properly made compost. The next slide. Where we don't add as much high nitrogen, the whole turning schedule might be set off a little bit. So it's really important for us to work with you to figure out the recipe. And so then every single time when it's going to need to be turned. Next slide. So as I said, we have that composting class that you might want to take if you're interested in making proper, real compost with all the right biology. So back to our program in Australia. We made the compost on farm, so there was no transportation cost, or very minimal, of just moving the on-site materials to the composting yard, make the compost, and then out it goes at 3 tons per hectare, or that's 1.5 tons to the acre. Typically after a grazing rotation in the autumn, where the animals were not going to be back on the property, on that field, for 30 days, typically. Again, we would check, just like we did back in Boston, we were checking the soil. What's missing? Make certain we're making a compost that's putting back in the missing organisms. And you can guess that they were trying to grow grass on dirt. So that to put everything back. In the springtime, then we checked again to make certain that the biology had come back the way it needed to be. And then 3 extracts, where we're just extracting the organisms from the compost or add a little bit of food, make a compost tea, about a month apart through the springtime period. In the first year, we started out with 5 farms, and I showed you pictures of 3 of those farms and some of the kinds of problems that they had. Word of mouth got out, and so from those 5 farms, in the second year, they had 74 farms working with the Camperdown Compost guys, doing this kind of approach. In the third year, it was 175 farms, and it's just blossomed from that point on. And it's because this is so against the commercial, conventional management practices, there's been a lot of controversy. A lot of work with Landline, which is the ag television station in Australia, lots and lots of presentations on Landline about this. Initially, if the farmer felt that fertility was inadequate, that the compost wouldn't be able to do the job, that they would still have fertility problems, we said to them that the grower could add liquid calcium nitrate or their pond water. No one ever had to do it. Because if you get the biology back into the soil, the biology is going to pull the nutrients that are present in your soil, in that organic matter as well, going to pull that and give it to the plant. There was no requirement in any of these instances where we had to come back in and add more material if, and here's the big if, they actually got the compost on and got the biology growing in that soil. There were a few people that didn't quite trust what we were doing, and they went out and put on an inorganic fertilizer, and then we could show them that they had killed their own organisms. They had shut down exactly what we were trying to do, because high levels of inorganic fertilizer are salts, and it kills the organisms. So next slide. Just some of the kind of, you gotta trust in the organisms. So here's their pastures in that first year after we've put the compost on. And
oh, Elaine, sounds like you cut out again. Let's make sure you're back on. Elaine, where'd you go? Hold on, let's get Elaine back on here. So everybody, a little technical difficulty. Okay, great. Unmuted her. Elaine, can you talk again?
Yeah,
all right,
here I am.
back on.
Okay, so we just got to this slide, and this is what the pasture looks like in that first year after applying the compost in the fall. And you can see how much clover has come up. All of these growers said it's the first time they had ever seen clover in their pastures. And of course, the veterinarian, the agronomists, they were all like, "Oh no, you can't grow clover. Clover causes bloat. You're going to kill all your animals. It's going to be just terrible." We never had any bloat in any of the animals, as compared to the conventional dairies that have all kinds of problems with bloat. The is that we're paid for the program, and just that all by itself was adequate to start moving people. So, and that's why next year we had 5 people, and the next year we had 74 people, and the next year we had 175 people, and it's just burgeoned from there. And one of the things they wanted to look at, because I was always talking to them about how far down do the root systems of grasses go. And they really firmly believed that the root systems of the grass didn't go more than 2 to 4 inches. And I always just said, well, that's because you tilled the soil when you resowed and you forced that compaction layer. And it's like, okay, let's dig into this. How far down do the root systems go? So here they are, they're starting to dig. Next slide. Hello?
Yeah, we're on the farmer's digging slide.
Okay, great. Yep, so there they are digging, and one of the things they started seeing were nodules on the root system of the clover. They had never seen that, because as soon as you put any inorganic fertilizer where you've got clover, it destroys the nodules. The rhizobium, the bacteria that forms those nodules, will not be invited into the root system by the plant if the plant has a luxury, high concentration amounts of the fertilizer. So it's the first time they ever saw those nodules. So if you go to the next slide, should be, there we are. How deep down did those root systems go? You can see that he's holding the top of the grass in the clover, and it's at about his hip height, and those root systems go all the way down to the soil. So where is the hip on a normal guy? We're looking at like 4 to 4.5 feet root depth in the first year after applying the compost and getting the proper biology going in that soil. And no problem with the clover, no bloat at all. Reductions in the veterinarian bills. So the next slide shows, I think, is the nodules. Most people think of nodules on clover as being little teardrop things. These are marble size. This is what you want to be seeing on your nitrogen fixing plants. And if your nodules aren't this size, you aren't farming in soil, you're farming in dirt. You can't raise good crops in dirt. We have to make certain it's soil. And here's another indicator for you. Your nitrogen fixing plants should have marble-sized nodules. When you cut these nodules open, they should be red in size. They should be like a drop of blood. If it's really fixing massive amounts of nitrogen, it should be the color of a drop of blood. And if it's just pink or you got little pinky veins, there's something wrong with your soil, and you need to fix those organisms. Next slide. So it was a big awakening for these growers. In this particular pasture, you can see that no nitrogen has been applied since the compost addition the previous December. Remember that this is Australia, and springtime is the middle of December. So May is fall. This is right before winter sets in. This pasture had been grazed 10 days before this picture. Look at how much the grass has grown. So these animals grazed that grass down and were moved on to another pasture. This is 10 days later. Look at how much that grass has grown. They could increase their herd size because the plant production was so much greater. Next slide. Just looking at how luxurious this is. There is no bare soil. There is nothing here where plants aren't growing. And so you can go ahead and increase your herd instead of decreasing herd size. There is no problem with moisture in the soil despite the fact that we're in the middle of a drought. So is it really a drought? Or is it because we've destroyed the ability of the plants to put their root systems down as deep as they should be going? Next slide. This is going back to the beginning. So this is the springtime after compost had been put on at the end of the growing season the previous May. So you can see all the clover that's come up, and you can see in the background, you can see some of the problems that they had. They have some significant weed patches. They've got problems with fertility. So this is where they're starting, and already we're seeing benefit. The next slide compares a neighbor's pasture with their pasture where they've put the biology on. So the left side is the neighbor's farm where they had to re-sow the pasture because it was basically bare soil. Nothing was growing. And so the left side is the neighbor's farm. The right side is the Whiting's farm after that fall time application of the compost going on. Now they're going to put on some compost extracts. Compost teas will go on through this growing season, but it's nowhere near the cost of the fertilizer. Pesticides do the different things that they had to be putting on otherwise. So look at how luxurious it is on the plus biology side. The no added biology side, that's looking pretty rough. Are you going to be able to run any of your animals on that pasture? Not looking the way it is, not unless growth picks up pretty fast. And look at the fact that the biology is sneaking underneath the fence. You know, go west, young man, young bacterium. Next slide shows later in the growing season. And so we're looking at, I always love it when you talk to growers. You say, take a picture in exactly the same place. And yes, they were taking a picture in exactly the same place, but they turned the other direction. So now the neighbor's pasture is on the right-hand side. They have grazed that pasture once, but it was not the full herd. It was only the pregnant cows that were put on that pasture. And you know, look at that pasture. That's you can't put anything on that pasture, there's not enough plant growth. The same on the other side. So the Whiting's farm field is on the other side. That field has been grazed 5 times between December and April. So which pasture do you want? Look at the background and tell me which set of pastures belong to the neighbors and which set of pastures belong to the Whitings. You can pick them out immediately because look at how green. So April is, very much late summer to early fall in this part of Australia, and yet look at how green and lush those pastures are still. Next slide shows the same paddock, and I think it's the same downhill picture. So almost, except it's on the other side of the fence. Growers. The Whiting's field is now being grazed 2 additional times. The neighbors have not grazed that pasture at all because look, you can still see where the grass was resown. The grass is not growing. It's not healthy. You look at the grass on the other side. See, it's not a soil problem. That grass isn't growing because the soil is poor. That grass on the neighbor's side is not growing because there's no nutrient cycling going on. There are no nutrients available. Those root systems are only going down 2 to 4 inches, whereas on the Whiting side, those root systems are going down 4 to 5 feet. So this is the kind of conversion. When we're talking about taking barren dirt and converting it into soil, healthy soil, it's this simple. It is not rocket science. It's not that difficult to do. But you do have to understand how to grow your own really beneficial organisms. So the next slide. Do we have time to keep going, or should we call this quits? Because I think we've been now at this for an hour and 3/4.
Just about. I think this is where we open it up to you guys. So to give you an example where we are in Elaine's amazing, mind-blowing presentation, she's about slide 44 out of 81. There's about 546 of you still here. Hanging in there, two hours in, and a lot of people are saying keep going. So Elaine, are you fine with doing that? Maybe
sure. I can talk about this all day.
All right, so we're gonna keep going. Thanks everybody for giving us your input. We appreciate it. All right.
Okay.
I'm gonna mute myself. Back to Elaine.
Okay, so some of the results, I don't have to read this. You can read it over. We're not resowing their pastures at all. That none of them have ever resown a pasture since they went on this program, because they're not buying the fertilizers, they're not buying the insecticides. Ultimately, those growers are saving over $200,000 a year because of what they are not applying, the reduced cost of applying. There's no fear from the EPA because they are not storing their manure in pits, in lagoons that stink to high heaven and cause disease and flies, and all of their non-dairy neighbors like them now because that stink and the fly population has dropped completely. One of the really interesting things is when we started out with these guys in the first year, 4% mycorrhizal colonization came back on the root systems of the grass, and it is now up at 87% of those root systems are colonized. So ever healthier over the years. Next slide, I think, just adds some more information about the benefits. Their tissue tests, everything's balanced. The plant material is balanced. Their Brix is now back up at 11 to 13 instead of down around 1 to 2, which is massive difference in food, in real nutrition for the animals. The insects are gone. The clover is inputting a lot of nitrogen into the system, even though we don't absolutely need it. It's way easier to let the organisms do this work for you. So just incredible. All the worms are back. You dig into their soils now, and there's worms everywhere. Whereas before they started adding the biology back, you could not find a worm anywhere on their farm. So got to get that biology back in there. So next slide. I think I have another example here. Yep, this is from an onion grower. Ian Smith in Tasmania. Yes, it's part of Australia, but it's the much colder part of Australia. This, Tasmania is a lot like the, up Iowa, Minnesota, that rung of states across the north. Yeah, cold winters. He had been conventional, his father had been conventional onion growers, and he wanted to see if all the fuss about biology was real. And of course, then we asked him what's his biggest problem. So think the next slide was what his problems were. Weeds. Weeds, that was destroying his profit. Oh, yeah, and he had some insect problems. Well, we asked him if he had any fertility problems, and what he said was, oh, no, I don't have any fertility problems because I put on inorganic fertilizer. And I just wanted to whack him one. You're putting on inorganic fertilizers and you're telling me you don't have a fertility problem? If you don't have a fertility problem, why are you putting on inorganic fertilizers? So you are telling me you have a fertility problem. Well, if you want to look at it that way, well, yeah. How about insect problems? Well, not really, because I put on insecticides. Ah, drive you crazy when you deal with folks that are just so into the conventional mode that they don't even recognize that this is a problem. Compaction was really his big issue. All of his soil was extremely compacted. We started pushing the penetrometer down into his soil, and he was at 300 psi to push a metal rod into his soil at about 1 centimeter depth, about half an inch down into the soil. So it's not soil, is it? It's barren ground. And now we've got to help him do that conversion. So the next slide shows, I believe, his that question of what is a weed, and people often get that they've fallen for the conventional fertilizer salesman definition of a weed. A weed is a plant that's out of place. No, because if I decide I don't want my oak tree here, then that oak tree is a weed. That's an absolutely ridiculous definition of a weed. Let's look at the ecological definition of a weed, and here it is. I think you can read this just as well as I can. Early successional plants that require massive amounts of disturbance. Weeds require just nitrate, strictly bacterial dominated soils. As you start to get the full food web back, as you start to get that balance of fungi and bacteria back into the soil, the weeds cannot germinate, they cannot grow, you do not have a weed problem. So reverse your, start putting a proper definition of weed into your mind. So next slide, I think is his picture, Ian's picture of his pasture, or not his pasture, his field paddock. In Australia, they don't call them fields, they call them paddocks. So field, I have to remember to switch terminology here. I look at this field, this is his onion field. His conventional paddocks, his conventional fields, were planted on exactly the same day as the field that we put 2 applications of compost tea on and would then apply 1 more. He's applied 2 applications of herbicide, and he has the conventional fertilizer that he went into all of his conventional fields, planted the same day. And I look at his onion field here and I go, where are the onions? And he kind of, you got to kind of look for them. If you get right along the row as you look down a little bit to the left of center in this picture, you can see the onions coming up. But really, is this an onion field or is this a weed field? He's going to have to get out here. He's going to have to put on the 3rd application of fertilizer. And don't ask me what fertilizer, fertilizer, herbicide. He's going to have to put on another application of herbicide. And I don't remember which herbicide he was putting on, but it was pretty toxic material. Any biology that was present in this soil before he started with a conventional fertilizer, so typically what he's putting on 450 pounds per acre of urea. They're typically putting on phosphate, and they're putting on some sulfate along with the herbicide, all of which destroys the biology in the soil. So let's compare his conventional system to the same field right next door Same soil, same everything. It had been in this toxic chemical approach. You can't find any weeds. This is what biology will do for you, but you have to get that shift from no biology to positive biology. You've got to shift it to a fungal component. So we want, with onions, we want about a ratio of 300 micrograms of fungal biomass, 450 micrograms of bacteria. So we go to the bacterial, go to the plus biology field. I'm seeing the conventional. Can we go
Sorry,
on?
we're on paddock 7. Yeah, let me move
Yeah.
over all the way. Did you hear paddock 12? Is that the right slide?
Nope, go back 2, and then just slowly go from, there we go. So here is paddock 12, where we applied the compost, the proper sets of biology, and shifted that fungal to bacterial biomass ratio. We had the protozoa in here, we were getting nematodes. Look at that field, there are no weeds. Look at the next slide. So we're, that whole entire, I think it was 150 acres, no weeds. So which paddock, which field is going to have the better onion yield? And he was just over the moon with delight in the fact that he didn't have to go out there and keep spraying herbicide. He didn't have to put out any inorganic fertilizer, and yet his onions, well, if we look at the next slide, I do want to point out he did this one treatment where he did not put anything over on that right-hand side that you're looking at. This is the field with the biology in it, and those are all onions that you're seeing coming up over on the left-hand side, but look at all the weeds. We did not put any treatment, so that's without the herbicide, without the fertilizers, and without the compost tea. So some people criticized initially, they said, well, he put his compost tea, there weren't any weeds in that field, so of course no weeds are coming up. Yeah, but if you didn't put the tea on, over there in that strip on the right-hand side, were there weeds growing in that field? Oh yeah. And so this is what biology does for you if you get it right. Next slide. Going back to paddock 7, where we were looking at the conventional system. These onion plants were planted on exactly the same day, exactly the same seed source, and yet when we're looking in paddock 7, the conventional system, this onion seedling is only about 3 inches tall, and you can see the root system doesn't even go as far down into the soil as the above ground part of the plant is growing up. There is severe compaction. Look at that. Well, it's not soil. This is dirt. There is no structure. There is no way water can infiltrate. There is no way oxygen is getting down deep, and the roots cannot grow as deep as they ought to. And look at the weeds. Who's winning here? Not the onion. It's the weeds. So on the next slide, we're going to be looking at the biological field. And we had to back off a little bit, so the perspective is a little further away than in the previous one, because in order to get the whole onion seedling into this picture, we had to back away. Look at how much better structured that soil is. There are aggregates, there are airways, there are passageways. That seedling is between 5 and 6 inches tall, despite the fact it was planted on the same day as a conventional system, and the root system of that onion is down at 1.5 feet into the soil because it can. Which of these onion plants are going to survive drought? Which of these onion plants are getting the nutrients that it needs every second of every day so there is no disease and the weeds can't grow in this field? So, next slide. So ultimately, we ended up putting on 3 compost teas. 2 of the teas, the good biology, went on prior to seeding and 1 post-seeding. So we work with a number of soil food web people in Tasmania that make really good compost, so you can go buy it. They didn't use herbicide during the time that we did the trial. So the grower said reduced herbicide because up until the first application of compost tea going out. Sorry, compost tea going out. There had been herbicides applied up to that time, but then as soon as we switched over to the biological approach, no more herbicides were put out. And so, very happy camper dealing with Ian Smith. So, next slide. I think that's. I just want to, one more specific topic is compost a fertilizer, because I got asked that. It depends on exactly what you call a fertilizer. In the chemical world, the conventional world, to be a fertilizer, you have to have the inorganic, soluble form of the nutrient. So your nitrogen has to be present as NO3, nitrate, or NH4, ammonium. Your phosphorus has to be present as PO4. Your potassium has to be present in inorganic, soluble form. Whereas when we're talking about biology, we want all these nutrients present in a not leachable form that will be converted into the soluble plant available form only after the bacteria and fungi get eaten by the protozoa and nematodes. And so you never have soluble nutrients that are in high enough concentration to be washed out of your soil and give you trouble with groundwater and with drinking water with your surface waters. So what is it that moves the nutrients from that not plant available form that might be in your sand, your silt, clays, rocks, and pebbles? In your organic matter, what moves it from those forms into the plant available form right around the root system? It's the soil food web. It's bacteria and fungi making enzymes to pull those nutrients out of the crystalline structure of the rocks, sand, silts, and clays, out of the organic matter, protozoa, nematodes, microarthropods, earthworms, predators in the system, releasing those nutrients right next to the root system. So how much is actually present in compost, in what form? So let's take a gander at, and if it's like every 10 seconds, you could just go to the next slide. Total nitrogen, look at how much total is in the compost as compared to a typical soil. We've got the two soluble forms of nitrogen here and then the total nitrogen. And it's just a massive amount of nutrient present in your compost. So you're only putting a ton of this out per acre, but you're still getting more nutrients per plant by putting out that compost than you would with any inorganic fertilizer application you would be putting out into that soil. Calcium, there's no reason to put lime out. There is no reason to put any nutrient out in fertilizers are just absolutely not necessary, or inorganic fertilizers are not necessary, because every nutrient your plant requires is in that compost. It's already in your soils, so why are we bothering?
Elaine, don't want to interrupt you. This is absolutely incredible. We're about 2 hours in. Neil had an idea, but how about let's do a Q&A. A lot of people are asking about the compost course, so we can do a little bit of Q&A, and then we can go back to this right after a quick Q&A session.
I think you can just kind of flip through these. There's just one or two more of these nutrient, and they get pretty boring after a while because it's like, okay, we got the idea. Just go on ahead until we're done with these nutrients, and then let's do Q&A. So there's calcium, phosphorus, woohoo, keep going. Potassium. So what nutrient does your plant need? Magnesium. It's there in massive amounts in the compost, and it's only going to be converted into that soluble form when your plant says it needs it. It's your plant that's in control of its life and its nutrients. Why do we think we know better what your plant needs today? So I think that's the last slide, isn't it? Okay, we can, so after we come back from our question and answer, and I might actually have somebody ask a question about this, so let's go into question and answer.
Sure. Oh, but before we do question and answer, a lot of people are asking about the compost course. So,
okay.
A lot of this is really cool. Elaine has a really, really cool offer that she was offering us for Life in the Soil classes, and this is amazing.
Yep. So what is it? The exclusive offer is half price off, is it?
It's half off. Carol said it was half off for all your classes, which was just awesome.
Yep. So typically the classes that we offer are the introductory course where we go through all of the organisms, what they do, all of the basic ecological theory, and really show you how to identify the organisms and get you to really understand all of the things that biology does for you in the soil. And then the next class is the compost class, where we go through the information that you need from a very practical point of view of how to make compost. When we talk about thermal composting, worm composting, and static composting. So your choice, which one's going to be easier for you to do. And then we go on to compost tea and compost extract, and then the microscope course. So you can be monitoring your own organisms. You don't have to be sending your samples into the laboratory and waiting, a week, 10 days, 2 weeks to get that report back. If you can do it yourself, it takes you about 20 minutes. When you get reasonably good at using that microscope, it takes you 20 minutes to assess your own biology, the bacteria, the fungi, the protozoa, the nematodes. Bad guy fungi, good guy fungi, good guy bacteria, bad guy bacteria, good guy protozoa, bad guy protozoa, good guy nematodes, bad guy nematodes. And right now, it's half off for you to do this. And I think it's for the next 5 days that if you sign up, you get the half price off.
Yeah, Carol said it runs till Monday, which is pretty
Next
awesome.
Monday.
Oh, by the way, all of this information is available in the handouts tab. It's got all the links. It has the presentation, everything that we're talking about. It's all in the handout, and we're going to email you the replay afterwards. So I think there's one more offer. Oh, man, here we go.
Yep. So for the whole group, it's more than a little bit more than half off. So we really want people to take these courses, understand that you don't have to be addicted to toxic chemicals in order to grow your plants. We will really benefit the environment and increase the nutritional concentration in your plants. So from a human point of view, we increase nutrients in the plants. A lot of the work that we've been doing, say with the Permaculture magazine, I've been writing a column for the last 3 months, and we've been going over all of the results of the experiments that we've been doing at the Environment Celebration Farm in Berry Creek in California, showing that when we add biology to the soil, when we're not destroying it through the use of inorganic fertilizers and pesticides, we are increasing yields by, on average, 300% compared to the conventional system. The highest increases in yields that we've had in squash, for example, we got 1,120% increase in yield by going with the plus biology as compared to no added biology into that dirt. So this whole idea of converting from barren ground into healthy soil, you increase yields, you increase the nutrient concentration, you get all of the organisms that you need in your gut microflora. Your microbiome gets replenished when you eat plant material that has the proper sets of microorganisms on the surfaces. And in order for you to be healthy, you have to have those organisms in your digestive system. Your only other choice is to go and buy some probiotics. And probiotics only have maybe 4 species of bacteria or 6 species of bacteria, when how many species of bacteria are there or should there be in your digestive system? It should be thousands. We need something like 75,000 species of bacteria in our digestive system. Where are you going to get them from? You're going to put back 4 species of lactobacillus. It doesn't cut the problem. It doesn't give you relief from the digestive system problems that we have. So eat healthy food. It starts with the soil. Healthy soil, healthy plants, healthy animals, healthy humans. So there we are. Lifetime money-back guarantee. Woo!
There we are. I'm going to jump in real quick before we get to the questions because I'm not sure how many folks attending now are aware of the work that I do, but I run an experimental farm on 100 acres in Saudi Arabia. And we average about 2 inches of rain a year. And the first time I looked through a microscope at our soil, it was 100% mineral. We had no life in our soil whatsoever. And we are transitioning from this experimental phase to a production phase where we've figured out what will grow there and what can grow there under some very abusive conditions. And now that we're moving away from that and moving towards having to produce and having to sell our products and turn this into a financially viable system, I'm in the process of taking Elaine's classes. I signed up for them with the last webinar that we did together, and I'm still going through them. But everything that I'm learning there are things I'm going to put into practice because we need so much biology kickstarting where we are just to get things to grow. And I'm in a bit of an extreme situation, but it's tremendously useful stuff and something that I, as someone who is working a farm in a very extreme climate, it's crucial. It's absolutely crucial for me. And so that's my personal endorsement of the things I'm learning in Elaine's class. It is going to save us thousands and thousands of dollars in our own operations in Saudi Arabia. And so I'm really thankful for that. And also really happy to be able to be part of the webinar that can offer this to folks. Because I do think it can move people along towards more sustainable systems and towards healthier systems. And I think that link should work. Some people were saying that the link wasn't working. We'll get that fixed and we'll send, if that one doesn't work, we'll find the right one and send it along.
Yeah, if anything doesn't work for anyone, send us an email. We'll send out a replay link with all this information in it, the slides, everything everybody wants. So I'm stoked. I'm really pleased that she would offer such a big, money back guarantee. That's lifetime. If anybody takes it at any point and they want their money back, they can have that. I think that's really cool.
And then I'd like to use my prerogative as one of the organizers to ask you some of the first questions, Elaine.
Okay.
The first being, because one of the things that I've noticed where we are is that we've had a lot of different kinds of mushrooms show up on the site that I'm working on, and I'm interested in your take on how the mycorrhizae interacts with the microorganisms that you're talking about, the nematodes and the protozoa. What's the relationship there between that fungal layer and between these microorganisms?
Typically, the fungi are helping the plant out by bringing nutrients, especially the mycorrhizal fungi, bringing nutrients to the plant directly, a direct pipeline. The plant tells the mycorrhizal fungus what nutrients to go out and collect. And of course, the fungus is out collecting its own nutrients, so it just adds a few more for the plant. But the plant is very clearly telling the mycorrhizal fungi what to bring back. And the mycorrhizal fungus makes the enzymes to pull those nutrients out of the sand, silt, clays, rocks, and pebbles, or organic matter, and pipes them right back into that plant. So healthier plant, healthier mycorrhizal fungus. It's a mutualism, symbiotic relationship. Now the protozoa are really impacting the bacterial populations. And it's important to keep the bacteria down to the proper biomass levels, because the bacteria and the mycorrhizal fungi, bacteria and any fungus, compete with each other for the food resources. And so we need to have the predators, the bacteria, to keep their populations down to the right ratio with the fungi. Bacterial feeding nematodes also serve part of that role of keeping the bacteria in control and not letting them get out of bounds and outcompete our fungi in those systems. Fungal feeding nematodes, of course, are going to be consuming any fungal hypha that they run across pretty much. And so there's got to be a balance between the fungal feeding nematodes and that actual fungi. There is predation there, so those fungal feeding nematodes are reducing your fungal population, but they do stimulate a lot of the fungi as well by releasing the nutrients and making nutrients, soluble nutrients, available back to those fungi. So it's all a question of balance in that system. We need to have higher level predators to keep the protozoa under control, to keep the bacterial feeding nematodes, fungal feeding nematodes at not too high. You know, nature operates on a Goldilocks principle. It's got to be not too low, not too high. And so what is it that prevents the fungal feeding or bacterial feeding nematodes, the protozoa, from overeating and wiping out all of the bacteria or all of the fungi? We have to have the higher level predators. So the earthworms, we've got to have the microarthropods. We need to have spiders. We need to have all those higher level predators in the system. And if you really think about that whole food web, as we add each layer, the organism that is at the top of that food web is us human beings. Our job is to be the gardeners of this planet. We're supposed to make sure that things are balanced correctly. That's our role and function. We're not here to exploit the planet. We're here to help nature do its job. And it's time we got around to doing what our job is.
To be stewards.
Yep.
Oh, Elaine, if you want to, you can try turning on your webcam now. I think your internet might have jumped up a bit, so
Okay.
yeah, try turning your webcam on. If there's any issues, we'll turn it off again, but let's see if we can see it.
Okay, I think I go right there.
It's that little video button below the microphone.
It's going to take me a few minutes to think about where that is.
Don't. How about we? If you see it, turn on. If not, we can keep doing Q&A with. Hey, there she is. Awesome.
There we go.
I figured out which button it is.
Yay! Oh man.
Right. Here's my second question, and then I'll be done, and we'll give it to everybody else in the audience. I'm looking at notes because I wanted to cite this correctly. There was an article in the journal Nature that came out in 2015 by some folks named Lemon and Kleber. And I read through it at the time, and essentially what they said essentially that there is no such thing as humic acid. Are you familiar with this article? They said
Well, part of the problem is that the way the chemistry world defined humic and fulvic acids were based on some pretty bizarre ways to extract the material. They take really strong acids and really strong bases in order to extract those very complex molecules from the soil or from organic matter, from compost, whatever, where the microorganisms have been doing this job of building those really complex organic compounds. And because it's, when you use really strong acids and really strong bases, it changes that organic matter. And so does humic acid or fulvic acid actually exist in that acid or base impacted form? And no, it doesn't. So it's kind of an artifact when you use those ways of extracting things from the soil. But you could say that about any of the soil chemistry tests that are done on anything.
Right.
When you do a test using Melic-3 extracting agent, and you say your soil has this much calcium or your soil has this much nitrogen or phosphorus, none of those compounds actually exist in the soil in the form that you're measuring them when you use a MELIC3 extraction, or if you use the Coleman, or if you use any of the extracting agents. So what? Nitrate doesn't actually exist in soil the way we're measuring it in our soil chemistry tests. So that's an artifact of the extraction method is a huge problem in soil chemistry. And when you think about how many different extracting agents are there for nitrate nitrogen, and which of those extracting agents actually give you the true concentration of nitrate in your soil, the answer is probably none of them.
Huh.
So which one do you use? So if these guys, the paper that you cited, if they would like to be honest about the rest of the way all of the things we extract from soil, they're all artifacts of the way we extract. Mm-hmm. So does NO3 exist in the soil? Sure, it does. But we don't really know how to extract it. So the only thing that we're getting from that soil is the NO3 that's in soluble form in the soil solution. Cool. And yeah, it's kind of mind-boggling a bit. But the fact is, very complex organic materials exist in the soil. And if you define it in a certain way, we can extract it using these strong acids, and we can quantify this very complex organic material. We can do the same thing for fulvic acids. If we extract with a base, then we can pull out these not as complex organic molecules, and they exist in the soil. Not in the form that we're pulling them out when we're pulling out humic or fulvic acid using these strong acids and bases. So it's kind of a semantics problem. The complex organic compounds exist.
Cool.
How do you want to define them, and exactly what is the structure of humic acid? The International Humic Substances Society has not yet come up with the actual structure of humic acid. We don't agree in the scientific world. So should we just keep arguing just let the scientists keep arguing. The rest of us are going to talk about fungal foods, and we're going to talk about bacterial foods. The highly complex, structured organic material feeds fungi. The very simple, not branched, not very complex organic compounds feed bacteria.
All right.
That's probably what we need to know.
That's my only erudite question of the day. Let's turn it over to everybody else. I'm going to disappear, but I'll be helping manage these. Raleigh, you want to take the...
You got it. Thanks for joining me.
Here?
I will take the helm and guide all of us, the 450 of you who are remaining, through these questions. So first of all of you, hundreds of you, 450 of you who stuck around for 2.5 hours to learn about restoring soil biology, thank you, because it just shows that you're people who really care, who really want to restore soil biology, so thank you for showing up. So here we go, 450 people left, and there's going to be a lot of questions. So if we can't get to all of your questions, we apologize. We're going to try to get to as many as we can. But just remember, there's a lot of people in here and a lot of questions. So for the first one, from Michael. So Michael asked an interesting question. He says, I don't understand why weeds do not flourish when the right biology is put in place.
I'm going to get into some chemistry here, and I hope you can bear with it. When we look at what bacteria do in soil, aerobic bacteria, they produce a lot of alkaline glue material around their bodies. And they have to make that glue so they can glue onto the surface of the root, or they can glue themselves onto the organic matter, on the surface of sands, clays, rocks, pebbles, because if they don't glue themselves onto a surface, they're going to get washed away with the water. As that water moves through the soil, the bacteria would get carried with it, and then the bacteria would no longer be able to grow because they're going to be removed away from their food resources. So the bacteria make glues, and those glues on aerobic bacteria, the good guy bacteria, are always going to be on the alkaline side. That means a pH above 7. So when we're in a soil that's bacterial dominated, more bacteria than there is anything else, the pH of that soil is going to be alkaline. And it is only under those alkaline conditions that the nitrifying bacteria are going to make the enzymes to convert soluble nitrogen forms into NO3. Only happens under alkaline conditions. Nitrifying bacteria will be there in acidic conditions, but they can't make the enzymes. The pH is not right. So if we're in fungal-dominated soils and acids, and so as there's more organic acid than there is alkaline glue material from bacteria, then we're going to see that the pH of the soil is going to be slightly on that acidic side. And as soon as the pH drops below 7, acidic, then the nitrifying bacteria cannot make the enzymes to convert NH4 into NO3. Ammonium is going to stay ammonium.
Elaine, really quickly, we're having a bit more of that robot voice with the pixelated visual. So how about you turn off the webcam and we'll just have audio. I'll go back to the presentation and we can just cycle through. But yeah, we'll keep doing Q&A.
Okay.
Okay.
That gonna work?
Yeah, it already sounds a bit better.
Good. So how much of the ammonium and fungi and bacteria did you get?
Did we get? Oh, no, we got most of it. It was just at the end it cut out a little bit.
Okay. So when soil is dominated by fungal biomass, when we have a significant amount, or as we start having fungi present, and that means now more of the soluble inorganic form of nitrogen is present as NH4 that cannot be converted to nitrate, weeds are going to be selected against. It is only in strictly bacterial dominated soils, very bacterial, very little fungi, that weeds can rule. Because those weeds, what they need are high levels of nitrate. As soon as some of that inorganic nitrogen is not converted into nitrate, it remains instead as NH4. That means not weedy plants have a chance to outcompete the weeds. They will start to rule. And the more we can get that fungal component up in the system, fewer and fewer weeds you're going to have. Gets to the point where there's not enough nitrate present, the seeds to even germinate, they won't even start growing.
Awesome. All right, so next question from Stephen. It says, have you looked at the impacts of subtherapeutic antibiotic use in dairy cow and other CAFO livestock? Aren't a lot of these antibiotics pooed and peed out? Wouldn't these pooped and peed out antibiotics have the same impact on soil microbes as they do on the animals? Or is there a way to clean out these antibiotics during the composting process? That's a good question.
Yeah, it is. Because most antibiotics are proteins, they are rapidly decomposed by bacteria or fungi. So in soil, for example, where you do have bacteria or fungi that produce antibiotics, they don't suppress for a very large area of soil. It's very localized. So even though it's soil organisms that make those antibiotics, they're not producing the massive quantities that we see in our medicines. So when we treat a cow, when we even you get an antibiotic, it's destroying the biology in your digestive system. Well, something in a cow, it destroys the biology in their digestive system, and I mean that antibiotic is going to be pooped out, the end of the human being or the animal. And we therefore need to be managing those waste materials properly. You have to have really good sets of microorganisms in high enough concentrations that we're feeding some really good foods to be able to deal with the antibiotics and decompose them. So if we're taking human, bio-sludge materials, if we're taking manure from cows or horses or chickens or pigs, or if we're feeding those animals antibiotics, and most feed this day and age, is treated with antibiotics to prevent bacterial and fungal growth in the bag of feed. That means we're harming the digestive systems of our animals. They can't take up the nutrients that they require because those antibiotics killed a lot of the beneficial organisms that do decomposition in the digestive system of those animals and allows nutrients to get into the animals the way they should. That's not happening. So even the animals materials that we're eating don't have the nutrition in them that they probably had 100 or 200 years ago. And their poop, what's coming out of them, is possibly high in those antibiotics. So we've got to compost things. We cannot take manure and put it directly on our agricultural fields because there are high amounts of antibiotics and other toxic materials in that manure. We have to compost it. In the composting process, because we're adding so much other non-antibiotic laden material, the green plant material, the woody plant material, the other high nitrogen plant containing materials, that those microorganisms using those resources have the wherewithal to chew up, decompose, consume, and get rid of those antibiotics. We have to be careful about what kind of antibiotic. So for example, deworming medicine is not really specific to worms, to parasites, to ascarid worms, things like that. It's not specific. And so it's pretty much a sterilant. And so you have to be careful. If you're using horse manure from a barn where they've just applied deworming medicine, you cannot use more than 5% of the total volume of that pile. It can be that horse manure with the deworming medicine in it. You got to be aware of some of those really toxic materials that people are putting in manures and in other waste materials. But it is why you cannot use manure straight onto your fields anymore, because it's so overloaded with salt, it's so overloaded with antibiotics and other toxic materials that you got to compost it. That's the only thing you can do.
All right, so Nick asks, you told us that the plants get all the nutrients from the soil food web interactions, and that's all the nutrients plant need in the soil. Is it true then that if you have the biology right in your soil, you never have to apply compost again to keep the biology right?
As long as you are making certain that you have plants growing in the soil. And so that constant input of exudates, of organic matter when the plant dies, when it loses its leaves, when the root system dies, you have to have that input of organic matter. So as long as we have plants growing in the field, in the soil, no, you should never have to use, even organic fertilizers would not be necessary. So you got to grow plants. And that is to a large degree why we really suggest that people put in very low-growing plants. So your whole entire soil is going to be covered with plant material, so that those exudates, those sugars, the proteins, the material that the life in the soil requires will be constantly maintained. So we're working a lot on what are these short, low-growing cover plants that are perennial. Once you buy the seed and you broadcast it and you get these plants growing in your field, you never have to replant them because they're perennial. They keep growing forever. They grow right through the winter times, a lot of time under the snow. And so, for example, here in California on the west coast of the United States, we're seeing the Dichondra repens, not the tropical dichondra, but the temperate dichondra, works extremely well. Mini clover works really well, and we're trialing a number of these other cover plants, and we need people all over the world that will test these cover plants. So we are constantly maintaining all this biology in the soil so that you do not ever have to add fertilizer. You're maintaining the growth of the microorganisms. If you don't have these cover plants, then you really want to think about making certain that the residues, when you harvest your crop, you leave the residues behind, that annual input of that carbon, those food resources for your bacteria and fungi, are going to serve to keep that biology alive and functioning. When you plant your crop in the springtime, okay, the exudate's coming out of the root systems of your crop, but what if you're not really planting a dense enough crop to maintain all of this proper activity of the biology in your soil? Okay, maybe that's where you need to be putting on at least compost. So you're putting in the food resources that will maintain this biology, or at the very least mulch, so that this food resource is coming back into the system once you have the biology properly balanced. Well, and then Mother Nature always comes along and throws, you know, a wrench in the system. She decides to send a snowstorm on the 4th of July. Whoops, you are probably going to lose some organisms, and you may then want to come back with a compost to replenish something that a really odd weather condition caused some of the organisms we need to be harmed and won't be there in your field. So lots to think about when you're trying to really manage this biology correctly. Okay?
All right, next question from Illyrian, and then we have a lot of questions interesting from coffee growers, but let's go to Illyrian's questions first. She says, "Hi guys, just want to say that I'm currently doing Elaine's course and they're amazing. I'm learning so much. Thank you, Elaine." She says, "One question, you mentioned before that we could take 1 grain of sand and spread all the nutrients around. It would be sufficient for 1 acre for 1 year. Can you expand on this a bit? How can this possibly be true?"
Well, when you look at the concentration of the nitrogen, phosphorus, sulfur, magnesium, calcium, all of that list in a gram of soil, typically, for example, nitrogen is present up around 2,000 to 4,000 micrograms of nitrogen in a gram of soil. And so if you take that small little bit, or just 1 grain of sand, you have enough nitrogen in that grain of sand to be putting out 200 parts per million of nitrogen over that whole acre. So just go back to your introductory soil science textbook and look at the tables of what is the nutrient concentration of every single nutrient in a gram of sand or silt or clay. And when you start to realize that just one of those grains will pretty much contain all the nutrients that an acre of plant material requires, you really get to the point of wondering, why do we put out inorganic fertilizers? But it's because we lost the biology. That's what the difficulty is. And when you think about your soil, is the sand, the silt, the clay replenished in your soil? It's replenished every day, every second of every day. Microorganisms are making the acids, they're making the enzymes to break down the rocks into the sand, the silt, the clay fractions. Your bedrock every second of every day is being broken down by bacteria and fungi into the component sand, silt, clays, pebbles, rocks, etc. So until the day that you run out of bedrock, you shouldn't have to put inorganic fertilizers back into your soil. That's just because the Green Revolution only occurred because we had already destroyed the biology in the soil. And again, go back to David Montgomery's book on dirt, The Erosion of Civilizations, and he shows over and over and over again how human beings have not understood how nature does things. And if we ever want to get away from losing our civilization, we've got to start paying attention to nature. Okay?
All right, next question. Let me get to this. It's from a bunch of coffee growers. Oh, by the way, I posted the right link in the chat box about the webinar offer. I guess I misspelled something in the handout, but I posted that in the chat box if anyone wants to take advantage of the offer. So here is a question from Timo, a coffee grower in Brazil. He says, "Hey guys, thanks a lot for the great webinar. I started to grow coffee in Brazil, and I'm working with England's farming systems. A lot of these things look very good. However, the coffee tree is a very sensitive plant, which can only be grown under several given conditions, and the climate predictions don't look good. For example, coffee needs 1,200 to 1,600 millimeters of water per year. Do you think in a good system this can be reduced, and where will the bottom line in your opinion be?" Sorry, one more question. What's the carbon to nitrogen ratio of coffee grounds? Thanks a lot. So
Um, I'll
it's
go
a
for the
long question.
easy. I'll go for the
Yeah.
easy answer first, and then we can have some fun with how do you deal with climate change especially when you have plants that have very specific requirements. The easy question is, what is the carbon to nitrogen ratio of coffee? And when you pick the berry is green. When it's straight off the vine, the ratio on that berry is typically 31. It's when we roast it, it turns brown at that point. And people will think that because it's brown, the carbon and nitrogen ratio is going to be very wide, and that's not the case. Because protein is decomposed, the sugars and the protein, the organic compounds in the roasted coffee bean. We now grind up that coffee bean. Well, we haven't lost any of the sugars and proteins. We're going to run water. We're going to extract the flavor compounds, or many of the flavor compounds in that when we prepare coffee. So we're losing quite a bit of those sugars, proteins, flavor compounds when we extract those coffee beans where a lot of the oil is being removed. So the grounds, okay, now grounds, we have removed a significant amount of those compounds, but it's been both the very complex oils as well as some of the simple sugars and proteins. So typically what's left when we're dealing with a coffee ground, once it's been extracted coffee, is something that still has a carbon and nitrogen ratio somewhere around, in my experience, around 40 to 1 or 30 to 1. That's green plant. That feeds bacteria. Some of the cellulose, some of the structural material in that coffee bean is more of a fungal food, but the majority of that ground, extracted coffee ground, is going to be bacterial food. So I hope that answers that question about coffee. Okay, now the other question was, and I'm hoping that you're still hearing me, right? Still hearing me?
Yeah. We had a thing. Your audio was chopping for a bit there, but I disabled your webcam, so it should be better now.
Okay.
Thanks for pointing that out.
Great. Okay, so now the question of coffee has some very specific requirements. And to a large extent, we want to put those plants back in control of their own habitat. So around that root system, we've got to let the plant direct its own life. Our job as human beings, when we want to grow specific plants in specific places in specific climates, is to recognize what that plant requires in the soil. Our job is to get that fungal to bacterial biomass ratio to be exactly what that cultivar of coffee requires. We've got to make certain that the protozoa, the nematodes, the earthworms, all of the normal predator organisms in that system are properly balanced, so we don't have too many or too few to eat the bacteria and fungi and get nutrient cycling going without destroying the bacteria and fungi's job of doing soil building, structure building, holding water in that soil the way that plant requires. we also have to have those predators in the system that will keep the predators of the bacteria and fungi in control. Maintaining those proper balances. Life is all about balance. So we need to know what those levels of each of those sets of organisms are for that particular cultivar of coffee. Coffee in general has some pretty overwhelming requirements, but each specific cultivar is different. So we've got to do some testing. We've got to do some work making certain that we know what this cultivar of coffee requires. So when you talk about drought, or you talk about it's too wet, you have very wet years, you have very dry years, you've got to make certain that the structure in that soil is such that every drop of dew is going to infiltrate into the soil, move down to a place where it's going to be held, where the root systems of our plants can get to that water if they need it. In really wet years, we've got to make sure that the structure of the soil allows proper drainage. And so the water-filled pores are only going to be that percentage of the pores that that plant requires. So getting that balance of bacteria, fungi, protozoa, nematodes, everything that builds structure within the soil. We've got a lot of work yet to do to fine-tune that kind of information for every cultivar that we want to be growing. So we've only begun. We have only begun to understand soil and the interactions of all these organisms. We have scraped the barest, tiniest depth of the knowledge that we someday have to have. And so we better get to work. We better get going on understanding this. Because if we don't, human beings aren't going to be alive on this planet. Okay?
All right, great. Thanks for that. So many questions. We had a question about, kind of lost in the thick of it, but it was a question about your methods for compost tea injection or compost injection. We had quite a few people ask about that. So
Right.
how does that work?
When we're dealing with perennial plants, you can't go back in and till everything up, because a lot of times if you have no perennials in the system, the simplest and easiest way of getting the biology back into the soil is to just till it in. Make certain that you till the compost in all the way down below all of the compaction layers that might be present in your soil. Okay, that's for annuals. But when we're dealing with perennial systems, we're going to have to inject that biology into the soil, or that's a very easy way to excuse me, break up all of those compaction layers. And so you need basically a pipe where there is a pump that is going to push the compost tea down that injector. And so at the tip of that pipe, you want to be able to have a hole. So it's going to release the compost tea, the biology that you want to deliver, as deep as you need it to be delivered. So typically somewhere around a 4-foot long pipe. That's easy enough for people to handle. So you push that injector. The pipe goes all the way down to the 4 feet. You pull back a little bit on the injector because you don't want to be smashing your organisms into the surface of that now compacted point of your soil. If you start pumping that compost tea out right against that compacted soil that you pushed against, you're probably just going to end up with bacterial and fungal slime. The organisms will burst apart, they will be killed. So you want to back off a little bit. And so as you pull your injector out of the soil, you want to be pumping the compost tea so that all of the sides of your hole that you produced is being coated with these really good sets of microorganisms. They're soaking into the sides of that pipe hole that you produced. So all the way up that injector hole. And then make certain that you spray a little bit of that compost tea out on the surface of the soil. And of course some of it will go down the hole, which just means you're continuing to inject the biology into that soil. How fast is the biology going to grow out from that hole that you put in the ground that you pumped all this really great biology in? And that's very dependent on how much structure was already present. If you're pumping into absolutely, completely, and totally compacted clay, the distance that that biology is going to be able to move is not that great, probably 3 to 4 inches going out from that hole. You might want to think about, what's the name of the fork? You put the fork into the ground and you move it back and forth, and you cause cracking and breaking in that soil surface. You might want to be doing some of that if you're in a really heavy clay. When you're pushing an injector into very sandy soil, you don't have to worry about that. You have to get your organisms to build structure in a sand so that the water doesn't just flow right on out and you really don't get much of the biology established before it's completely dry again. When you're injecting into really heavy clay, you gotta try to break open and get cracks and crevices happening in that soil so that the organisms can build structure. So now you have airways and passageways to allow oxygen and water and your organisms and your roots to grow into that material and start building the structure. So I hope that answers the question.
That was a great answer. All right, so Stephanie asked, how many inches of compost are needed per acre? I know you said 1 ton per acres, but of course the compost company said that amount seems pretty low. They recommend at least 2 inches.
Yeah, you really want to think about what is your purpose in applying this compost. If you're really applying the compost to get organic matter back into your soil, well, it would be way less expensive probably to go buy mulch and then mix that mulch with the compost, because really the compost is the biology that's in there. That compost it's an inoculum. And the great part about biology is it reproduces. You just have to feed it. It just has to have some water. And biology is going to go ahead and reproduce. And so you really only, if you got enough biology in your compost, you really just need to put a dusting on the soil surface. Now, how far down is that biology going to be able to move? Look at the compaction. If you've got really bad compaction right at the surface of the soil, the compost, those organisms, is not going to be able to move very deep into the soil. Here at Berry Creek, we bought the property here because the people who had owned it before us were absolutely crazy about applying all kinds of toxic materials, or somebody was crazy. Most of the garden area wasn't even growing any plant. It was bare, not even weeds were growing in the area. So is this dirt? Is this barren ground? Absolutely. So part of the study that we did was to apply the compost, the extract, just to the surface of the soil. And we knew compaction was right there at the surface. We were over 300 psi at about a 1/4 inch into that soil in some places. And if you apply just to the surface, it only moved into that soil. The soil structure was only built about 1 inch into the soil in the first year. In the second year, that biology only improved soil down to 2 inches. But that's how bad that soil, well, that's how barren that soil was. In places where it's not that bad, your compaction's not 300 psi right up here at the surface of the soil, then putting a dusting of compost out with really good biology. We have documentation of places in Idaho, for example, where compost tea was put on the soil surface, and within 4 weeks, 6 weeks, we had rebuilt the structure all the way down to 4 feet. So when people ask me these questions about how rapidly the biology is going to move into the soil, or really isn't it kind of too minimal putting on just a ton per acre? you got to go back to the standard ecological aspect. It all depends. You got to know what's in that dirt, how bad the situation is in that barren ground, or it's not so bad, you've got some good biology. So take samples from your soil and find out how bad things are. Get that penetrometer out there and find out where your compaction layer is. Do you need to be tilling? Do you need to be injecting down into the ground? But if you've got not that bad, things just need a little perking up. You need to improve fungi just a little bit. You got to get some protozoa in there. A dusting of really good compost with really good biology, that's all you need. You got clay that is like layers of brick on the surface of your soil. Okay, you're going to have to till, you're going to have to inject, you're going to have to do something to get that really good biology further, deeper, to move into your soil, and that's probably going to take more than a ton per acre. Okay?
Awesome. Okay, so a few technical questions about equipment. Oh, this is tough. A lot of you guys have such awesome questions, but there's hundreds and hundreds and hundreds of them that are very, that are paragraphs long here. So, again, I'm down to be on here as long as you want. Elaine, is all up to you, however long you want to answer these. But Silas asks, what compost tea brewer do you recommend? I remember you talked from PV2, but kicked myself later for not taking notes on that particular topic. I remember you had some really bad things to say about most brewer designs.
Yeah, it's when I look at a brewer, what I want to do is make certain that it doesn't have a closed top that you can't get off, because you got to get inside that brewer to clean the thing. You cannot have biofilm that is accumulating anywhere. Remember I was talking about bacteria and how they have to have glue to not be washed away from the surface. They like to be stuck on surfaces. And so, of course, your bacteria, when you're brewing your tea or you're extracting your tea, those bacteria are gluing to the surfaces of that compost tea brewer inside. And you've got to be able to take your high pressure washing system, thumb in the end of the hose, or you can get fancier, and you got to blast those surfaces off. Well, if you have a closed top where you can't get that high pressure washer going on the inside of your brewer, you're not going to be able to clean the biofilm off, and pretty rapidly you're not going to be making good tea. So, clients of mine where they have bought brewers that have a full plastic top, and it's just that little tiny opening where you can screw on a lid or screw it off. I just go get my saw and remove the top. Go get a big board. Go get a piece of plastic to just put on top of it if you're concerned about birds flying over your compost tea brewer and pooping in the water. Right, like that happens a lot. But if you're concerned, you can always just find a flat piece of board and put it on top. Not a problem. But you got to be able to get into that brewer in order to clean it. You want nothing inside the brewer. You don't want pipes, you don't want air stones, you don't want anything that you're going to have to clean after every tea brew. You don't want anything with holes, or if you don't mind spending time cleaning stuff like that, then okay, just make sure it's minimum. Absolutely no air stones. You cannot clean the inside of an air stone. There is no way to do that. And so after 5 or 6 tea brews, you can't make tea. So there's a lot of you got to think about those things. You also want to look at how the air pump that you've got and make certain that it's an air pump that is moving the water around, and it's got to be enough air movement so you're getting a rolling boil on the surface of the water. You do not want the fountain effect. You start having your waters blowing up into the air 2 or 3 inches or out of the brewer. You are going to be slicing and dicing and ripping your organisms apart. So rolling boil, but not blowing the water up into the air. What else? You want to you want a compost bag or container where all of the compost will be moving as the water is moving up off the bottom from the bottom of the tank through the motion of your air pump. Um, so all of the compost in the bag is moving and swirling and moving, all the organisms are being extracted off all of those surfaces of that compost. If your compost is sitting in a lump at the bottom of your bag, you've got too much compost in that bag. Reduce the amount of compost by half. Keep reducing it until you know that that compost is all in suspension, mixing and moving around in that bag. So there is no point in having compost that is in a bag that's completely compacted. You are not going to be able to make good tea. So, a lot of those things in the compost tea and extract class, I go through all of these things, all of the factors in the sprayers and the pumps and and a lot of times, because I'm a microbiologist, I work with organisms. I don't necessarily understand all the mechanical equipment all that well. We have a lot of folks that we've been working with on these systems, and I will direct you to work with some of the people who are specialists with the different kinds of pumps, the fusion pumps or the centripetal pumps or the air pumps or the sprayer systems, because I don't know everything. And there's no way I can know everything. So I will pass you on to people who do know so that you get your questions answered to the best possible. Okay?
All right, good question. All right, next question is from John Brown. Do you use keyline plows along with biology injection and seeding in certain situations to speed up soil creation?
Absolutely. Yeah, I think the keyline plow is a great invention, or yeoman plow. Only the thing you want to do in addition is to down the back side of the shanks that are going down into the ground, you want to put like a PVC pipe. It can't be real wide diameter because you don't want movement as you're pulling your keyline plow through the soil. You don't want the PVC pipe to be pulled off the back of the shank. You got to be careful on the diameter of the pipe. You just need little holes in that pipe. Pointing out in back of the pipe and to both sides, so that as the keyline plow is moving through the soil and it's the wings on the bottom of the keyline plow cause that shank to twist a little, wiggle back and forth, and it causes a lot of cracks and crevices to appear all that whole depth down that you've got the shank going. And the biology needs to be squirted. It needs to be pushed through down all of those cracks and crevices. So you are really going to expand the distance around each one of those shanks. And so a much larger volume of your soil is actually inoculated with this really good biology as that keyline plow is being moved through the soil. Worked a fair amount with somebody in, I think it's Tennessee, the Keyline Cowboy. And he has shown huge improvements in yields with pastures, with grapevines, with a number of vegetable crops. And so I would probably direct you to work with him, or, like a number of the permaculture folks that use the keyline plow. Darren Doherty is another one. So there's quite a few people who are doing this system and showing really good results, really improved yields and structure in the soil, roots going down way deeper, because they're combining the use of the aeration that you get when you use the keyline plow with inoculating the biology into that soil at the same time. Okay?
Okay. All right. So, next question from Aaron. Dear Elaine, I would very much like to know your take on potential benefits, concerns of Streptomyces colonization, particularly the strain Streptomyces nigrensis MR541, on the uses of inoculated substrate as a top dress to create a mycelial mat. Cool.
Streptomyces is an actinobacterium. So, you know, I would probably have to go back and look at whatever reference he's referring to. I rarely like just one organism because it's any one particular species of anything only works in a very limited set of conditions. We need a massive diversity of organisms because we always want the work that needs to be done every second of every day, or every single time that work needs to happen. We've got to have somebody there doing that work. And if you're relying on one particular species, a mat of one individual species present, it's only going to function for a very short period of time, especially when we're out in the real world or we're in greenhouse conditions where things change all the time. So I don't like just one species going out. I want to see a massive diversity. And so what is the point exactly of that particular Streptomyces? Is it antibiotic production? Is it? So that's I kind of have to ask back to him exactly why would you be putting that particular species out, and why would you want a huge biomass of just that one species? There's probably a good reason, but I'm not aware of it. So darn it, I can't manage to read everything in the world of microbiology. There just isn't enough time in a day.
All right. Question from Leslie. She sent me an email a few days ago. She says, I'm starting a project here in Spain. Most of the properties are bare dirt olive groves. The other problem is that there used to be a forest fire here about 8 years ago that it was extinguished with seawater, and she's trying to restore that. Is there anything we should be looking for when trying to get analysis done?
What she's really going to need to do is get organic matter back in that soil. The seawater that was used, so high salt concentration, to have something that microorganisms can take that sodium and that chloride and other nutrients that are now in high concentration because of the use of salt water. She has to have a carbon substrate that those ions can be put back into the structure of that organic matter, which means you've got to have some carbon chains. You've got to have some organic matter for the microorganisms to have a place to store those ions. Forest fire, she's probably got a lot of charcoal in the ground, or there might be, unless it's all blown away in the intervening years where nothing's growing on the soil, it's still bare, and most of it may have blown away. But even with charcoal, for that to get turned into soil, the microorganisms have to be present. They're going to have to build structure with charcoal material. When the high temperature and low oxygen concentrations, which occur when you have a forest fire, when that wood material is burning, that's going to produce some pretty toxic materials quite often, and you've got to have biology to deal with those toxic materials. The charcoal may have a lot of nutrients in it, but a lot like your bedrock, it takes enzymes, it takes the microorganisms to decompose that material to pull those nutrients out. So life is required, and life requires food. So both of those things need to go back in. That might be one of the places where they'd want to consider a pretty good mulch layer tilled into that substrate. And at the time that you are tilling, you would want to be applying a really good compost tea or If you have enough compost, put the compost in, because compost not only has the organisms, but it's got a lot of this organic matter um, in it as well. This makes me think of the times when we've gone around to municipal composting areas, or waste reduction facilities is really what we should call them, and tested a lot of what they're selling as compost. We looked at hundreds of samples. When I was working in Australia, we looked at lots and lots of compost from all over the country. Here in the United States, we've done the same thing. South Africa, England, France, lots of places in the world. And it's always appalling to me when you get the organic matter content of a compost, or something that's called compost, and you realize that it's only 10% organic matter. The rest of it is sand, silt, and clay, rocks and pebbles. And that's not compost. You can't expect good results with something that is not organic matter. So with our compost, we have to make sure that it's just organisms and organic matter, and we don't have other stuff in there. And I think the reason people put clay, or they put other materials into the compost, is to make it heavier, so they're going to make more money when they sell it, because compost is pretty light stuff. And we should only be paying for the organic matter and the organisms in that material, not a whole bunch of inert material. So just one of those things that always astonishes me when I deal with compost and discover that it's only 10% organic matter. Okay?
All right. All right, question. So this is from a lot of New Zealand farmers. So Toby Schweikert asks, most farmers here in the hill country in Taipei, New Zealand, are farming sheep and cattle on steep land. It would be impractical to apply compost. Would an application of compost tea be enough to make a difference on the land?
Absolutely. Yeah. So when you're dealing with steep land where you put the solid material on that, and the next time it rains, it's just whoosh down into the lower elevations. Yeah, that's just not going to work. So yes, a compost tea. Most of the time, when we're going onto soil, we're going to put a compost extract, because those organisms don't have to stick immediately. You apply that compost extract onto the soil surface, it immediately gets taken up. If you've got any kind of structure at all, that material is going to get taken up. The organisms move into the soil, and the organisms are going to find that place where their foods, their conditions that they are going to grow in are met. Injection is also another possibility when you're dealing with real steep slopes, except that you now have to walk those steep slopes, and that can sometimes be very difficult to get out there and do an injection. There are machines, and especially in New Zealand, if you talk to, I'll remember, Cheryl Prue, they have a machine where they can do injections along a hill slope like that. You've got to talk with them and find out what the requirements are for that machine. But on both sides, the injectors go down, so as you're driving along, even on a slope, depends on how steep your slope is, that machine will work for doing those injections when you're driving along. So check her out. Cheryl has the Soil Food Web Laboratory down in Roxborough on the South Island. So you might look her up on Soil Food Web New Zealand. Okay?
Okay. Question from Dave. You mentioned actinobacteria help protect roots from root-feeding nematodes. Do actinobacteria help to clean up the soil, sequester loose nutrients, give soil its fresh, clean, earthy smell? Or are they harmful to mycorrhizal fungi?
Yes. Okay, yes to which part? Actinobacteria, of course, it depends kind of answer, whether it's really beneficial or whether it's detrimental. If you're trying to grow brassica, or if you're trying to grow the cole, kale, mustard, many of the lilies are non-mycorrhizal plants. Some of them are mycorrhizal. So you have to know the requirement of the plant that you're trying to grow. So very early successional riparian kind of plants typically do extremely well with the actinobacteria, because actinobacteria are suppressive. Many, not all, but many of them are suppressive to mycorrhizal colonization. So if you want to make certain that your brassica, cole, kale crops, mustards will not become mycorrhizal because it's detrimental to them to become mycorrhizal, make certain you've got good actinobacteria levels in your soil. And that may be where, the question about the streptomyces came from. Very beneficial for certain reasons. But if you're trying to grow a plant that requires mycorrhizal fungi, you do not want a high component of actinobacteria of any kind in that soil. It's quite detrimental to those particular plants because it suppresses the ability of the mycorrhizal fungi to colonize the root system. So having an understanding of the biology required is a really necessary thing, and I think in the classes that we offer, I go over that concept again and again and again, and have lots of visual pictures, lots of explanations of how to figure out what kind of mycorrhizal fungi your plant requires, or what kind of actinobacteria your plant requires.
All right, so we had a good observation from Kent. He says, when are you going to let Elaine go? She sounds like she's getting tired. How are you doing over there? It's only
I'm going to
3.5 hours in, but
I'm going to have to go to the restroom pretty soon.
Okay.
So I think maybe 2 more questions.
2 more questions. All right, let's make them good questions. Okay, I'll try to take 2 good questions. Here we go. Looking back. Okay, what are your thoughts on aquaponics? Can you create nutrient-rich plants even when there's no soil? Yeah, so question about
Absolutely.
aquaponics.
Yeah, absolutely. When we do a lot of nutrient trough work, or float tables, when we do flood tables, you just have to have this really good biology in the water solution. So generally we'll add a compost tea or a compost extract to the holding tank, and then as that liquid moves through your system, these organisms colonize on the surfaces of the roots. The bacteria and fungi, of course, are going to bind and be held on the surface of those roots, and then that provides the habitats, the aggregates, for the protozoa and the nematodes to be present on those root systems as well, and they are what set up that nutrient cycling. You're going to have soluble organic material that you are allowing to run through the system, and generally what most people use is humic acid that has been extracted with water from the compost. So there's all of the chemicals, the nutrients that your microorganisms need. So as that humic acid passes by your root system, the bacteria and fungi are making the enzymes to grab those nutrients and pull them into the aggregates on the surfaces of the roots. The bacteria and fungi then hold and retain all those soluble nutrients that are now in the bacteria and fungi. Bacteria and fungi are eaten by the protozoa and nematodes, and that, of course, is releasing those plant soluble nutrients right there next to the root system, so your plant takes them up. It is not the concentration of the nutrient in the water, so you don't have to have these massively high nutrient concentrations in the water that's moving through the whole system, which of course helps select for disease-causing organisms. And that's, in aquaponics, hydroponics, that's usually what takes you out, is that overnight some pathogen gets going and just poof, the next morning you walk in and everything's dead. So we don't want to have that happening. We want to have very low concentrations of the nutrients in the water that's passing through. the system, but you want all this nutrient cycling happening right on the root system. So that root is a solid surface. And so all your microorganisms are going to be hanging out there. And that's all that's necessary when we're doing aquaponics or hydroponics.
Awesome. You guys are all chance for sticking around 3.5 hours. Oh, amazing. And thank you so much, Elaine. Before we get to our last question, I have to give a shout out. We're going to send this webinar replay email. You're going to get all the links, the presentation, everything we mentioned. That's all going to be in the email, so watch out for that. And in case you didn't see it before, here's the offer for the Life and Soils class. And if you want to sign up for more webinars like this, our website is sustainabledesignmasterclass.com. And we do a webinar. We try to do it at least once a week, but at least we do it twice a month with amazing folks like Elaine Ingham. So let's do it. Last question. How about we turn Elaine's webcam on so we can see her face for the last question. Oh, this is tough. I have to decide between two. But Seth Peterson asked, the permaculture chef Seth Peterson, the local logger from Berkeley, asked, what are your thoughts about natural Korean farming?
There is a lot that's very positive about natural Korean farming because they've understood that, you know, the toxic chemicals in conventional agriculture are so very detrimental. But you know, I'm a scientist and I've got to know why things work, not just, well, you know, we threw this out there and good things happened. I want to know why good things happen because I want it to be repeatable. I want to know every time I do this that it's going to result in something positive. And so I want to be doing assessment of the biology that's present in that soil. You really need to have the microscope and be able to monitor what the biology is and not just cross your fingers and hope. For example, in natural Korean farming, they suggest the use of rice balls. And so you take a ball of rice and you throw it out into the forest, and that's supposed to collect really good fungal diversity. Well, how many food resources are there in rice? How many different fungal species actually grow on a ball of rice? Very few. So are you getting the diversity that you require in your compost pile or in your agricultural system when the only thing you're using to collect diversity is a very limited resource of food? We really want to go out to that forest system and take small pinches of really good fungi, all the different kinds of really good fungi that you can see with your eyeball, and take just small, very small amounts of that, bring it back, inoculate that into your compost pile. So in case you happen to pick up a really nasty pathogen when you were doing your collecting from that, what you thought was a healthy natural system, which in fact wasn't perhaps, we want to make certain all of those species go through that composting process. So we get rid of the pathogens, the pests, the parasites, the human, parasitic organisms don't get enhanced, and you're not adding those out on your soil surfaces. You're not putting them into your agricultural system. We need that filter to get rid of the problem organisms and making sure that just the good guys are going out into our soil. So I think, we need to add that biological assessment to know that what you're doing in Korean natural farming is really giving you the results that you want. Their hearts are in the right place. They are doing exactly, doing very good things for the most part. But I'd add in, let's make sure that we know that what we're adding are very beneficial organisms.
All right,
okay?
Awesome. Hey, do you have time for one? There's one really interesting question we can answer really quick.
Okay.
We got to go to the restroom. Matt Fallon asks, have you worked with bioslurry effluent from a biodigester for compost teas?
Not for compost teas, because that effluent from anaerobic digester, digesting plants has some really nasty compounds in them, any anaerobic process, especially where the point and purpose of an anaerobic digester is to make methane or to make hydrogen gas, really nasty anaerobic conditions, there's some really toxic stuff coming out. And we've got to compost that. That has to be properly dealt with. Now, if you make really good compost with that material, it can be tricky. So you got to be careful of what you're doing and really understand the organisms and what they do. We can turn that into good stuff, and then you can make really good compost tea with it. But it's, again, got to go through that filter of turning it into something aerobic, where all the beneficial aerobic organisms are growing, the full food web is present, and that can be really tricky. I've worked with a number of people who work with anaerobic digesters, and man, we have killed more worms than you want to think about. Even a tiny bit of that anaerobic digest material going onto the surface of a worm bin can just kill absolutely every worm in the bin. You got to compost it first.
Compost! Okay. Compost
yes. We must have our organisms.
All right, Seth had, he's like, no, wait, one last question. What's a good inexpensive micropost to buy? You don't have to answer that if you don't want to. Only if it takes 2 seconds.
A microscope? Is that what the question was?
Inexpensive microscope he can buy.
Yeah, if you go to our website, we have a link to microscope.net, and that's the least expensive but very good microscope. Just don't buy the built-in microscope camera anymore. Buy the microscope that has the light pipe on it, so you can buy your own camera and software for taking pictures of the organisms. But the link that we have on microscope.net, they make the best microscopes for the least amount of money. Typically, they will run you without the camera on it, without the light pipe on it. They run about $300. With the additional light pipe, they're about $325, $350. It depends what time of year. If you go to buy the microscope just before Christmas, they usually have specials. So right now we're a little past Christmas though, so go and take a look, see what's available. A lot of times you can find them used on Amazon or eBay or something, so you might check that out. Okay. That's it.
I desperately. Hero. Go. You got to do what you got to do. Thank you so much for joining us.
Thank you. Well, thank you so much for doing this. I so much appreciate all of your time and effort into putting these webinars together. Thank you.
No, I appreciate having you on here. Thank you so much, and enjoy the rest of your day. You deserve it.
Okay. Take care.
Right. Ciao. Ooh, man, thank you so much, everybody, for sticking around. 3.5 hours. You guys are champions. Just champions. I appreciate all and every one of you showing up, giving your time because you really care. And Neil and I are going to keep putting these out there. We're going to keep putting out classes. And we're really open to suggestions. I want to do things that help everyone create more interaction because we love you all. We're here because we're all on a mission because we know something's wrong in the world, and we want to create better livelihoods for ourselves while we restore a very troubled environment. So thank you for joining us. You're going to get an email with everything, replay. That's for free. It's available till Monday. Offers available till Monday. And you guys have an amazing day. Hopefully you get some outside time, play in your garden, play in your soil. Have an amazing day. Sustainable Design Masterclass out. Peace. All right, I'm going to stop the recording right now.